How did faint, star-like points reveal some of the most powerful engines in the universe? What force could outshine entire galaxies from a region only light days wide? Why did the discovery of quasars forever change our sense of cosmic scale? Long before astronomers knew what powered these beacons, the night sky held points of radio light that mocked their instruments. In the early years of radio astronomy, catalogues like the Third Cambridge Catalogue listed hundreds of sources. Many entries were messy patches that corresponded to known galaxies or remnants. But within the tables were a few perplexing dots that looked like distant stars, bright on radio maps, yet faint in visible light. Observers could not say if these dots were nearby or remote, new or old. They were simply unresolved points that refused to behave like anything else in the surveys. In the 1950s, pioneering radio telescopes swept the sky and assembled lists such as the 3C catalogue, its revised 3CR version, and the 4C survey. Each survey pushed sensitivity and positional accuracy forward, reducing the sea of static to distinct sources. Yet the more carefully astronomers looked, the more they found objects without obvious optical counterparts. With instruments still coarse, it was hard to tell whether these puzzling sparks coincided with stars or nebulous fuzz. The early lists became treasure maps pointing to mysteries rather than answers, leading observers to cross-check at different wavelengths. Optical astronomers joined the chase with large telescopes and photographic plates. They tried to match radio positions to faint stellar images, often failing because of poor coordinates. Some successes emerged, such as the identification of Cygnus A as an optically faint galaxy with strong radio emission. But the oddest sources defied classification. They looked like normal stars, but their spectra were unlike any star known. The printed charts showed them as points with no nebulosity, and their brightness did not match any known class of variable star. By the early 1960s, 3 of these radio points, catalogued as 3C48, 3C196, and 3C286, were tied to star-like images. Thomas Matthews and Alan Sandage used the Palomar 200-inch telescope to photograph the sky at the radio positions and found faint, blue stars at each location. These were not ordinary stars because they seemed slightly extended and had unusual colors. With curiosity aroused, the astronomers took spectra to search for familiar absorption lines. Instead, they encountered broad emission features at wavelengths that did not correspond to any known atomic transitions. The confusion deepened when these star-like radio sources changed brightness. In some cases, their optical intensity varied by significant amounts over months or years. No known star or nebula behaved this way while also emitting strong radio signals. The spectral lines were broad and fuzzy, hinting at motion or turbulence. For a while, some scientists speculated about gravitational redshift or exotic new physics. The patterns did not resemble anything in the spectral atlases, leaving researchers to puzzle over what they had discovered. More precise positions arrived thanks to lunar occultations. Occultation occurs when the moon passes in front of a distant source, allowing timing measurements to refine coordinates. In 1962, radio astronomer Cyril Hazard used this technique to pinpoint the radio source 3C273 as a star-like object not far from the ecliptic. Alan Sandage then identified a 13th magnitude stellar object at the predicted location. Its optical brightness and variability suggested something extraordinary. With the stage set, a young Caltech astronomer named Martin Schmidt took the critical step that would reveal the nature of these enigmatic points. Schmidt obtained a high-resolution spectrum of the optical counterpart of 3C273. When he examined the plate, he noticed broad emission lines at wavelengths slightly longer than known hydrogen lines. After puzzling over the pattern, he realized that the lines matched the Balmer series of hydrogen if the entire spectrum were shifted toward the red by about 16%. This redshift implied that 3C273's light was stretched by the expansion of the universe. Such a shift corresponded to an immense recession velocity, placing the object billions of light-years away. Recognition came slowly, because the idea was so startling. If 3C273 lay 3 billion light-years distant and yet appeared as bright as a nearby star, its intrinsic luminosity must be colossal. Schmidt's calculations showed that the object was roughly 40 times brighter than any known galaxy. Soon afterwards, the puzzling lines in the spectrum of 3C48 were also interpreted as a hydrogen spectrum with a high redshift. The term quasi-stellar radio source, or QSR, entered the lexicon to describe these radio emitters that looked like stars but were not. As more spectra were taken and the redshift interpretation gained acceptance, astronomers realized that these quasi-stellar objects were much farther away than any previously observed active galaxy. The redshifts corresponded to distances of billions of light-years, meaning the light left the sources when the universe was young. At such distances, even small apparent sizes implied tremendous physical size and brightness. The object's energy output exceeded the combined light of hundreds or even thousands of galaxies. This discovery redefined the cosmic distance scale and challenged ideas about how much power the universe could muster. Naming these objects soon followed. The phrase quasi-stellar radio source was cumbersome, and not all of these objects were strong radio emitters. In 1964, astrophysicist Hong-Yi Chiu proposed shortening the term to quasar. His suggestion, published in Physics Today, caught on. Within a few years, the community adopted quasar as the standard name for these quasi-stellar beacons. The new name was snappier and better suited to the rising number of discoveries. Even with the name settled, basic questions remained. What powered these compact engines? How could a source generate so much light in such a small region? The redshift measurements suggested that the energy source must be extraordinarily efficient to outshine entire galaxies. Early ideas included supermassive stars or gravitational collapse of clusters. As data accumulated, the concept of a supermassive black hole feeding on surrounding matter emerged as the most plausible engine. The gravitational energy released by infalling gas could convert a significant fraction of mass into radiation, explaining the extreme luminosities. Spectroscopy continued to play a crucial role. The emission lines in quasar spectra were not only redshifted, but also very broad, indicating that the emitting gas was moving at thousands of kilometers per second. These motions implied a deep gravitational potential well. In addition to hydrogen lines, spectra revealed elements like carbon, nitrogen, and oxygen at various ionization states. Some quasars showed strong ultraviolet emission, and others exhibited absorption features, hinting at clouds of gas along the line of sight. Each new spectrum added nuance to the picture of a dynamic, compact region surrounding a central engine. Distances derived from redshifts shocked astronomers accustomed to much smaller cosmic scales. The famous 3C273 resides roughly 2.3 to 3 billion light-years away, depending on the cosmological parameters used. Even at that distance, it is bright enough to be seen with amateur telescopes. This fact underscores its extraordinary luminosity. The early redshifts of 0.16 for 3C273 and 0.37 for 3C48 correspond to velocities and distances far beyond those of known galaxies at the time. The knowledge that tiny points of light could be so distant transformed perceptions of the observable universe. As the number of known quasars grew, astronomers noted that their apparent magnitudes varied. Some brightened or dimmed over months, others over days. A few exhibited changes within weeks or even hours. This variability indicated that the emitting region must be compact. A source cannot vary faster than the time it takes light to traverse its diameter. If a quasar's brightness doubled within a week, the emitting region must be only a few light weeks across, yet the energy output of that region equaled the combined light of a galaxy. Such a combination of enormous power and tiny size defied conventional astrophysical objects. Variability served as a crucial clue in understanding quasars. Observers tracked light curves and looked for repeating patterns. Some quasars flickered irregularly, while others exhibited quasi-periodic outbursts. These changes offered insights into the dynamics of the central engine and the accretion of matter. Rapid variability also bolstered the case for a compact, relativistic engine, like a black hole accreting matter, because only such an object could radiate so intensely from a region just a few light days across. Without variability studies, the true scale of the power source might have remained hidden. Another emerging distinction was between radio-loud and radio-quiet quasars. About 10% of quasars emit strong radio jets extending across thousands of light years, while the majority emit relatively little radio energy. Radio-loud quasars often show large, double-lobed structures in radio images, with jets carrying energy away from the core. Radio-quiet quasars lack such pronounced jets, and their radio emission is weak or absent. This division pointed to differences in magnetic fields and the orientation of the central engine. Understanding why some quasars launch jets while others do not remains an active area of research. The concept of an active galactic nucleus expanded beyond quasars. Seyfert galaxies, named after Carl Seyfert, are nearby galaxies with bright cores and prominent emission lines. Blazars are extreme objects whose jets are aimed nearly toward Earth, leading to strong variability and polarization. Radio galaxies host jets and lobes that can extend millions of light years. These diverse phenomena were unified by the idea of a central supermassive black hole surrounded by an accretion disk and, in some cases, a dusty torus. The viewing angle and strength of the jets determine the observed characteristics. In this unified picture, a quasar is an active galactic nucleus in which the central engine is particularly luminous and may or may not be radio-loud. Seyfert galaxies are similar engines embedded in spiral galaxies. Type 1 Seyferts show broad emission lines, while Type 2 Seyferts display narrow lines because their broad line region is obscured by dust. Blazars are quasars or radio galaxies viewed along the jet axis, causing the jet emission to be Doppler-boosted BL-lac objects. A subclass of blazars have very weak or absent emission lines and show rapid variability. This unified scheme helps interpret a wide range of observations with a single underlying structure. In radio astronomy's early days, the instruments were simple arrays of dipole antennas, recording fuzzy patterns on chart paper. Astronomers took pride in crafting equipment from surplus radar gear, often in barns or fields far from cities. They learned to distinguish the sun's hiss from cosmic noise and to recognize the signature of Jupiter. When the first catalogues were compiled, each source was a small victory. The 3C catalogue recorded 471 sources. The 3CR revision refined positions and fluxes, and the 4C survey added thousands more. These lists were compiled with patience and ingenuity, laying the groundwork for deeper exploration. Stories abound of observers braving cold nights at the focus of giant dishes, adjusting wires and coaxial cables while scanning for elusive signals. Many sources were soon identified with supernova remnants, H2 regions, or known galaxies, but a handful remained unresolved. The radio points 3C48, 3C196, and 3C286 were particularly intriguing. They were bright on radio maps, yet had no obvious counterparts in photographic surveys. For years they resisted classification, their true nature hidden behind instrumental limitations and the sheer novelty of radio astronomy. When Matthews and Sandage matched 3C positions with optical plates, they discovered faint bluish points at the radio locations. These star-like images lacked the fuzziness of distant galaxies and did not show proper motion like nearby stars. The suspicion grew that they were something entirely new. Observers took spectral plates and found broad emission lines that did not match any known atomic transitions. For months they puzzled over these lines, considering whether they might come from heavy elements under extreme conditions. Some even speculated about unknown physics or gravitational effects altering the light. The sense of mystery was palpable. In the case of 3C48, the spectrum showed large emission features around 4,000, 300 and 5,000 angstroms. No known combination of elements produced such lines in a star. The idea of a massive object within our galaxy radiating unusual spectral lines held sway for a while. However, the lack of proper motion and the radio brightness suggested an extragalactic origin. When Schmidt later re-examined 3C48 after solving the redshift of 3C273, he recognized those features as shifted ultraviolet lines from carbon and oxygen, confirming that the object lay billions of light-years away. Each spectrum thus became a Rosetta Stone unlocking cosmic distances. The technique that enabled the final leap was lunar occultation. By timing when a radio source disappeared behind the moon's limb and reappeared, astronomers determined precise positions. Hazard's occultation of 3C273 provided coordinates accurate enough for Sandage to locate the optical counterpart. Schmidt then took a spectrum with the Hale telescope. On the plate, he saw 4 broad emission lines spaced like the Balmer series of hydrogen, but all shifted to longer wavelengths. Recognizing that simple pattern required intuitive brilliance. Once he accepted the redshift interpretation, a door opened onto an unimaginable scale. The surprise lay not only in the redshift, but in the implications for luminosity. If 3C273 was receding at about 16% of the speed of light, cosmological models placed it billions of light-years away. Schmidt calculated that its intrinsic brightness was equivalent to tens of trillions of suns. 3C273 outshines the entire Milky Way, yet it occupies a region smaller than a solar system. Such concentrated power demanded a new kind of engine. The discovery forced astronomers to accept that the universe harbored sources far more energetic than anything they had encountered. Even after Schmidt's discovery, some astronomers remained skeptical of the cosmological redshift interpretation. Alternative explanations included gravitational redshift near a compact object or ejection of material at relativistic speeds. Some suggested that quasars might be local objects with unknown gravitational properties, perhaps ejected from nearby galaxies. Over time, however, the weight of evidence from many quasars with consistent redshifts and host galaxy associations convinced most researchers. The simplicity of the redshift explanation and its alignment with Hubble's law eventually prevailed, though debate persisted in some quarters for years. The term quasar itself emerged from practical necessity. Journalists struggled with the awkward label quasi-stellar radio source. Hongyi Chu proposed quasar in a 1964 Physics Today article, arguing that a short, memorable name would aid communication. The suggestion resonated with both astronomers and the public. Soon the name graced headlines and research papers. In adopting the term, The community acknowledged both the star-like appearance of these objects and their distinctiveness. The name also signaled a turning point, marking the moment when quasars took their place as a major astronomical class. Before black holes were accepted as the engines of quasars, other hypotheses were explored. Some researchers imagined gigantic stars called supermassive stars, held together by radiation pressure. Others proposed dense clusters of neutron stars or white dwarfs. Yet these models fell short when confronted with the observed luminosities and variability. Only a supermassive black hole could convert sufficient gravitational energy into radiation from a small region. As theorists developed the mathematics of accretion disks, they showed that infalling gas spiraling into a black hole could radiate with efficiencies up to 10%, far higher than nuclear fusion in stars. This theoretical work complemented observational evidence and cemented the black hole paradigm. In quasar spectra, the broad emission lines are produced in gas clouds moving at thousands of kilometers per second close to the black hole. These clouds form the broadline region, which may be shaped like a flattened disk or a series of orbiting clumps. Beyond this zone lies the narrow line region, where gas moves more slowly and emits narrow spectral lines. Dusty material further out forms an obscuring torus. Depending on our line of sight, the torus can block the broadline region, leading to different spectral types. The unified model thus explains Seyfert-1 galaxies, Seyfert-2 galaxies, and quasars within one framework. Redshift, the stretching of light to longer wavelengths, is a key tool in quasar studies. It arises because the universe is expanding, causing light from distant objects to be stretched as it travels. The redshift value, denoted by Z, measures how much the wavelength has increased. A quasar with Z equals 0.5 means its light has been stretched by 50%. For small z, redshift relates linearly to distance via Hubble's law. At high redshift, relativistic cosmology must be considered. Observing quasars at Z greater than 6 allows us to see the universe when it was less than 1 billion years old, giving glimpses of the early cosmic dawn. The distances implied by quasar redshifts lead to profound time travel. Light from a quasar at Z equals 2 began its journey when the universe was about 3 billion years old. We observe it after 9 or 10 billion years of cosmic expansion. Thus, quasars act as time capsules, carrying information from epochs long past. Their light encodes not only the conditions near the black hole, but also the intervening intergalactic medium. Absorption lines in quasar spectra reveal clouds of hydrogen and metals along the line of sight, mapping the distribution of matter across billions of light years. In this way, quasars serve as beacons, illuminating the cosmic web. The sheer luminosity of quasars defies everyday experience. Some shine with the equivalent of thousands of Milky Ways, producing more energy per second than all the stars in our galaxy combined. Popular articles often compare a quasar's brightness to trillions of suns, numbers almost impossible to fathom. If a quasar were placed at the distance of Pluto, its light would vaporize Earth. Fortunately, they reside billions of light years away. Such staggering energy output underscores the efficiency of the accretion process and the extreme nature of the central engine. It also raises questions about how this energy influences the environment around the quasar. Understanding the power of quasars requires comparing energy production mechanisms. Nuclear fusion, which powers stars, converts about 0.7% of mass into energy. Accretion onto a black hole can convert up to 40% of rest mass energy for spinning black holes. This difference explains how a small region can outshine an entire galaxy. The gravitational potential energy of infalling matter is enormous. As gas spirals inward, it heats up and radiates across the spectrum. Magnetic fields extract rotational energy and collimate jets. These processes make quasars cosmic particle accelerators, accelerating electrons to relativistic speeds and producing synchrotron radiation visible in radio wavelengths. Early models posited that quasars might be local objects with large gravitational redshifts due to massive compact objects. However, gravitational redshift alone could not account for the observed spectral features or the uniform distribution of quasar redshifts across the sky. Moreover, gravitational redshift near a compact object would produce asymmetrical broadening of lines, which was not observed. The cosmological interpretation elegantly explained the correlation between redshift and faintness. High Z quasars were more distant and therefore dimmer in apparent magnitude. As more data accumulated, the cosmological model became the consensus, with alternative models fading into obscurity. Quasar variability manifests in different ways. Long-term variability occurs over years and decades as accretion rates change and structure in the accretion disk evolves. Intermediate variability spans months, often reflecting instabilities in the disk or the movement of hotspots. Rapid variability can happen over days or even hours, implying small emitting regions and perhaps relativistic beaming. In radio-loud quasars, flares correspond to shocks in the jet. In blazars, where we look down the jet, outbursts are particularly dramatic and can double the brightness in a single night. Monitoring programs track these variations to study the physics of accretion and jet formation. Photometric monitoring campaigns use networks of telescopes around the world to obtain continuous light curves. By correlating optical, radio, and X-ray variability, astronomers test models of how energy propagates through the accretion disk and jet. Reverberation mapping measures time delays between changes in the continuum and responses in emission lines. These delays reveal the structure and size of the broadline region. Shorter delays imply closer clouds, while longer delays indicate more distant gas. Such studies provide a spatial map of regions that cannot be directly imaged due to their small size. Some quasars exhibit microvariability or intraday variability, with changes in brightness on timescales of hours. These variations may be caused by turbulence in the accretion disk or by interstellar scintillation, where the signal is modulated by the interstellar medium. Intraday variability has been observed in both radio and optical wavelengths. Its presence confirms that at least part of the emission arises from extremely compact regions. Studying these subtle flickers requires high-precision photometry and careful separation of intrinsic variations from observational noise. The rewards are insights into the smallest scales of quasar engines. The distinction between radio-loud and radio-quiet quasars is central to understanding their diversity. Radio-loud quasars launch powerful jets that emit synchrotron radiation detectable across the electromagnetic spectrum. Their radio images reveal twin lobes extending far beyond the host galaxy, often connected by narrow jets. Radio-quiet quasars lack such prominent jets and have radio emission 100 times weaker. Yet they are not silent. Some radio-quiet quasars do have small, compact radio cores. The difference may arise from black hole spin, magnetic field strength, or the rate of accretion. Determining the cause of this dichotomy is an ongoing challenge. Jets themselves are marvels of astrophysical engineering. They consist of charged particles accelerated to near the speed of light and confined by magnetic fields. Jets can extend hundreds of thousands or even millions of light years, carrying energy away from the central engine. Shocks within the jets produce knots and hotspots that radiate at radio and X-ray wavelengths. When jets interact with surrounding gas, they inflate lobes that glow in radio light. The orientation of the jet relative to our line of sight determines how bright and variable a source appears. For blazars, the jet points almost directly at us, so we see dramatic flares amplified by relativistic beaming. Approximately 1 in 10 quasars is radio loud. The fraction remains roughly constant across cosmic time. The reasons for this minority status are debated. One idea is that a high spin rate of the black hole enables the formation of stable, powerful jets. Another possibility is that mergers and environment influence jet production. Dense gas may quench jets, leading to radio quietness. Observations of quasar-host galaxies support the idea that radio-loud quasars are often found in elliptical galaxies, while radio-quiet quasars can inhabit spirals or ellipticals. The correlation between host type and radio loudness hints at deeper connections between galaxy evolution and quasar behavior. Radio-quiet quasars, though lacking prominent jets, are not less important. They dominate the quasar population and therefore shape the overall luminosity function. Their energy output is carried mainly by radiation rather than jets. Radio-quiet quasars show strong optical and ultraviolet emission lines and contribute to the ultraviolet background that helps ionize the intergalactic medium. They may host winds that carry material away from the nucleus, producing broad absorption lines in their spectra. Such winds can influence the host galaxy by removing gas that would otherwise form stars. Understanding radio-quiet quasars is essential for a complete picture of black hole growth and feedback. Active galaxies come in several flavors, unified by a central engine. Seyfert galaxies, first catalogued in the 1940s, are common in the local universe. They display either broad or narrow emission lines depending on orientation and obscuration. Radio galaxies are dominated by large radio lobes and jets. Blazars are extremely variable and polarized sources with jets pointed toward us. Quasars occupy a region of high luminosity and can be radio loud or quiet. This taxonomy reflects differences in power, environment, and viewing angle, but does not imply fundamentally different engines. The unified model ties these classes together in a coherent framework. Blazars themselves are subdivided. BL Lacertae objects, named after the prototype BL Lacertae, show very weak or absent emission lines and often have low redshifts. They exhibit rapid variability and strong polarization. Optically violent variables, another type of blazar, show stronger broad emission lines and tend to lie at higher redshifts. Both types display extreme variability because we are looking down the jet, amplifying fluctuations. Observing blazars helps us study jet physics and the processes that accelerate particles to ultra-relativistic speeds. Radio galaxies are massive ellipticals with bright radio lobes. They come in two main morphological types. Phaneroff-Riley type Y sources have bright cores and fainter, diffuse lobes. Type 2 sources have hotspots at the edges of bright lobes and often more powerful jets. These differences may reflect the jet speed and the environment. Radio galaxies, quasars, and blazars can be considered part of a continuum. A quasar, with its jet seen at an angle, appears as a radio galaxy, while the same object viewed along the jet axis appears as a blazar. This unified perspective simplifies the apparent diversity of active galaxies. The golden age of surveys owes much to improvements in detectors, computers, and optics. Early radio surveys used large dishes and analog recorders. Later surveys employed aperture synthesis, combining signals from multiple antennas to obtain high-resolution maps. Optical surveys transitioned from photographic plates to CCDS, dramatically increasing sensitivity. Fiber-fed spectrographs allowed astronomers to obtain spectra for hundreds of objects simultaneously. Data pipelines reduced raw images to catalogs. The synergy between instrumentation and data processing made it possible to survey millions of objects and identify tens of thousands of quasars. The 2-degree field instrument on the Anglo-Australian telescope was a milestone. It used robotically positioned optical fibers to collect light from up to 400 targets at once over a 2-degree field. During the second F-quasar redshift survey, observers spent clear nights positioning fibers on faint blue objects selected from photographic plates. The survey covered 2 long strips, each 75 degrees by 5 degrees, on either side of the galactic plane. Over 5 years, the 2DF team gathered spectra for more than 20,000 quasars. This dataset enabled statistical analyses of quasar clustering and luminosity functions at redshifts between 0.3 and 2.2. From the second F data came insights into cosmic homogeneity. Quasars were found to be more numerous at higher redshifts, peaking around Z approximately 2. The spatial distribution of quasars traced large structures hundreds of millions of light-years across. These structures aligned with those seen in galaxy surveys, confirming that quasars inhabit the same cosmic web. The data also indicated that bright quasars were rare in the present epoch, supporting the idea that black hole accretion rates decline over time as galaxies mature and gas supplies dwindle. The 2DF survey thus connected quasars to the evolving universe. The 2SLAQ survey extended quasar studies to fainter magnitudes. By allocating spectrograph fibers to dimmer targets, it compiled spectra for more than 5,000 quasars over just over 100 square degrees. The survey aimed to refine the faint end of the quasar luminosity function and to test predictions of hierarchical galaxy formation. Early results revealed that the number of faint quasars increased rapidly toward lower luminosities. This suggests that many quasars operate at modest luminosities, perhaps due to lower accretion rates or smaller black hole masses. Surveys like 2SLAQ fill out the population statistics necessary for understanding the full range of quasar activity. Radio surveys such as the Very Large Arrays First Survey and the NRAO VLA Sky Survey mapped radio emission across large swaths of sky. These surveys identified thousands of radio-loud quasars and provided high-resolution images of jets and lobes. In combination with optical surveys, radio catalogues allowed astronomers to match radio sources with optical counterparts and study the environments of radio-loud quasars. The combination of radio and optical data helped test unification models and explore the relationship between jets and host galaxies. Infrared surveys like the 2-micron All-Sky Survey and the Wide-Field Infrared Survey Explorer revealed quasars obscured by dust. Dust absorbs ultraviolet and optical light, but re-radiates energy in the infrared. Some quasars are heavily reddened and thus escape detection in optical surveys. Infrared surveys found these hidden quasars, showing that a significant fraction of black hole growth is obscured. Spitzer and Herschel observations extended the quasar census into the mid and far infrared. The discovery of dust-enshrouded quasars highlights the importance of multi-wavelength observations for a complete picture. The Sloan Digital Sky Survey transformed extragalactic astronomy. Its imaging camera used 5 filters to measure fluxes in different bands, producing multicolor images over thousands of square degrees. Automated pipelines selected quasar candidates based on their colors and fed them to spectrographs for confirmation. SDSS produced spectra for hundreds of thousands of galaxies and over 100,000 quasars. The scale of SDSS's quasar sample, hundreds of times larger than previous compilations, allowed for refined measurements of quasar clustering, evolution, and diversity. SDSS's baryon oscillation spectroscopic survey aimed to measure the subtle imprint of sound waves from the early universe in the distribution of galaxies and quasars. It obtained spectra for over 500,000 galaxies and more than 100,000 quasars, up to redshift 3 quasar spectra from BOSS, revealed absorption by intervening hydrogen clouds, known as the Lyman alpha forest. These absorption features trace the density of the intergalactic medium and allow measurement of baryon acoustic oscillations at high redshift. The result is a cosmic yardstick for gauging the expansion history of the universe. Beyond SDSS, surveys like Pan-STAR-RS, the Dark Energy Survey, and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time continue the mapping of the quasar population. With deeper imaging and larger sky coverage, these projects will find millions of quasars, including many at Z greater than 6. These high redshift quasars probe the epoch of ionization, when the first stars and galaxies ionized the neutral hydrogen, filling the universe. Each new quasar, discovered at high redshift, extends our view further back in time, closer to the cosmic dawn. The accumulation of quasar samples has spurred sophisticated analyses. Stacked spectra combine light from thousands of quasars to produce an average spectrum with high signal-to-noise. Such composites reveal features like Phi-2 emission blends and subtle absorption troughs. Principal component analysis identifies patterns in quasar spectra and helps classify them based on emission line ratios and continuum shapes. Machine learning algorithms mine large catalogues to discover rare types of quasars, such as those with extreme accretion rates or unusual chemical abundances. With big data, the study of quasars has become both statistical and exploratory. Quasar number counts show that their space density rises dramatically from the present to redshift around 2, then declines toward higher redshifts. This evolution is understood in the context of black hole growth and galaxy evolution. During the peak epoch, abundant cold gas fueled rapid accretion, leading to luminous quasars. As time progressed, star formation consumed gas, and feedback processes ejected or heated it, reducing the fuel supply. By the present day, only a small fraction of galaxies host active quasars, and those tend to be less luminous. This evolutionary trend mirrors the history of cosmic star formation and suggests a deep link between black hole growth and galaxy assembly. High redshift quasars, with redshifts greater than 6, are rare but invaluable. The first such quasar was discovered in 2001, with a redshift of 6.28. Since then, dozens more have been found. These early quasars harbor black holes with masses exceeding 1 billion suns. Their existence challenges models of black hole formation because there is little time in the early universe to grow such massive objects. Possibilities include rapid accretion at rates near the Eddington limit, collapse of massive gas clouds, or formation from the remnants of massive population 3 stars. Each high redshift quasar is a laboratory for understanding the birth of supermassive black holes. Quasars play a key role in the epoch of reionization. Their intense ultraviolet radiation can ionize hydrogen gas in the intergalactic medium. Observations of the Lyman alpha forest in quasar spectra show that the universe transitions from mostly neutral to highly ionized between redshifts 6 and 7. Measuring the fraction of neutral hydrogen at different redshifts provides clues about the timing and duration of reionization. Quasars themselves likely contribute to ionization, but their number density may be too low to dominate. Instead, young galaxies and their stars probably supply most of the ultraviolet photons. Nonetheless, quasars remain critical probes of this cosmic milestone. Beyond reionization, quasars aid in measuring fundamental cosmological parameters. The absorption lines in quasar spectra reveal the fine structure constant and its possible variation over cosmic time. Lensed quasars, where a foreground galaxy splits quasar light into multiple images, provide time delays that can be used to estimate the Hubble constant. Quasar clustering data feed into measurements of the matter-power spectrum. As luminous, distant objects, quasars act as standard rulers and candles in ways complementary to supernovae. Their usefulness extends well beyond the study of black holes to the fabric of cosmology itself. The absorption features, imprinted on quasar spectra by intervening gas clouds, are rich in information. Each absorption line corresponds to a specific transition of hydrogen or a metal ion, shifted by the redshift of the absorbing cloud. By measuring the depths and widths of these lines, astronomers deduce the density, temperature, and chemical composition of the gas. The Lyman alpha forest arises from numerous small clouds along the line of sight, tracing the filamentary structure of the cosmic web. Damped Lyman alpha systems, with much larger hydrogen column densities, correspond to nascent galaxies rich in gas. Metal absorption lines reveal the enrichment of the intergalactic medium by previous generations of stars. Gravitational lensing adds another dimension to quasar studies. When a massive galaxy lies along the line of sight to a quasar, its gravity bends and magnifies the quasar's light, producing multiple images. Time delays between variations in these images allow measurement of the Hubble constant and probe the distribution of dark matter in the lensing galaxy. In some cases, lensing amplifies very distant quasars, enabling detailed spectroscopic study that would otherwise be impossible. Lensed quasars also provide a natural laboratory for microlensing by stars in the lens galaxy, which can probe the structure of the quasar's accretion disk. Quasars offer tests of relativity and fundamental physics. The broad iron K alpha line observed in X-ray spectra arises from fluorescence of iron atoms in the inner accretion disk. Its shape and redshift encode information about the disk's velocity and the curvature of spacetime near the black hole. High-frequency quasi-periodic oscillations in X-ray light curves may correspond to orbital frequencies near the innermost stable circular orbit. Measuring these features tests predictions of general relativity in the strong gravity regime. Some observations hint at the spin of the black hole, which influences how efficiently the accretion disk radiates and how powerfully jets are launched. In recent years, astronomers have begun to study quasars in the time domain more systematically. Time domain surveys, like the Zwicky Transient Facility, monitor large areas of the sky repeatedly. capturing the light curves of thousands of quasars. With these data, researchers can search for periodic signals that might indicate binary supermassive black holes. Such binaries would arise from galaxy mergers and may emit gravitational waves detectable by future observatories. Variability studies also identify changing-look quasars, objects that transition between Type 1 and Type 2 spectra as the accretion rate changes. These phenomena underscore the dynamic nature of active nuclei. The interplay between quasars and their host galaxies is intimate. Quasar host galaxies often show signs of interactions or mergers, such as tidal tails and disturbed morphologies. Mergers funnel gas toward the center, triggering starbursts and feeding the black hole. In turn, the black hole's radiation and winds can heat or expel gas, suppressing further star formation. This feedback may explain the observed correlation between black hole mass and bulge velocity dispersion, known as the M-sigma relation. Quasars may thus regulate the growth of galaxies, acting as both beneficiaries and agents of galactic evolution. Quasar winds reveal themselves through broad absorption lines, BALs, in ultraviolet spectra. BAL quasars show deep, blue-shifted absorption troughs from highly ionized species like C4, SI4, and N5. These troughs indicate outflows of gas moving at tens of thousands of kilometers per second. Some BAL quasars show low ionization lines, low BALS, or even ion absorption, FEL-OBALS, pointing to a rich range of outflow conditions. The covering fraction of BALS suggests that winds may be present in many quasars, but are only visible along certain lines of sight. Outflows carry mass, momentum, and energy into the host galaxy and intergalactic medium, influencing their evolution. As the number of known quasars increased, classification schemes multiplied. Researchers grouped quasars by their spectral properties, radioluminosity, optical colors, and variability. Some categories, like red quasars, exhibit significant dust extinction. Others, like narrow-line Seyfert-1 galaxies, show narrow permitted lines and are thought to host low-mass black holes accreting at high rates. The diversity of quasar spectra reflects a combination of intrinsic differences, such as black hole mass and accretion rate, and extrinsic factors like orientation and obscuration. Recognizing patterns in this diversity is key to understanding the life cycles of quasars. The story of quasar discovery would be incomplete without mention of the human element. The excitement of uncovering a new class of object is palpable in historical accounts. Astronomers recall the thrill of watching broad emission lines appear on photographic plates, the frustration of trying to identify unknown spectral features, and the satisfaction of solving the redshift puzzle. The early debates over cosmological versus gravitational interpretations were heated yet collegial. The adoption of the term quasar shows the importance of communication and imagination in science. Behind the numbers and spectra lie the stories of individuals whose curiosity drove them to look deeper. Quasars remind us that the universe is dynamic and evolving. What begins as a faint radio speck can turn out to be a beacon from a young universe. The light of a quasar travels across billions of years, carrying with it the imprint of cosmic history. When we study quasars, we connect with eras long before the Earth formed. We also find parallels between cosmic and human timescales. The flicker of a quasar over a few days echoes the brevity of a human life compared to cosmic epochs. Such reflections lend a philosophical dimension to astronomical research. The interplay between observation and theory in quasar studies is an example of the scientific method at its best. Observers collected data without knowing what they were seeing. Theorists proposed models, some of which were soon discarded, others refined. Each new observation either confirmed or challenged existing ideas, driving improvements in instruments and analyses. The eventual convergence on the black hole model required contributions from many disciplines: relativity, plasma physics, nuclear physics, and more. The journey from puzzling sparks to a comprehensive model exemplifies how science progresses through collaboration and persistence. X-ray observations have opened a new window on quasar physics. Satellites like ROSAT, Chandra, and XMM Newton detect the high-energy emission from hot gas near the black hole. The X-ray continuum provides information about the corona, a region of hot electrons above the accretion disk. Reflection features reveal the geometry of the disk and its inner radius. X-ray variability is often faster than optical variability, hinting at processes occurring closer to the black hole. Some quasars, particularly radio-loud ones, also emit gamma rays detected by instruments like Fermi, showing that jets accelerate particles to ultra-relativistic energies. At longer wavelengths, millimeter and submillimeter observations probe cold dust and molecular gas in quasar hosts. Telescopes like ALMA resolve structures in the host galaxies and detect emissions from CO and other molecules. Such data reveal the amount of gas available to fuel both star formation and black hole accretion. Observing dust emission helps estimate star formation rates in quasar hosts, showing whether they are undergoing bursts of star formation or are quiescent. The interplay between star formation and black hole growth is a central theme in galaxy evolution. Infrared space telescopes have been instrumental in detecting dust-enshrouded quasars. The Wide Field Infrared Survey Explorer, WISE, catalogued hundreds of millions of objects across the sky. Its data revealed populations of obscured quasars that are almost invisible in optical light. Mid-infrared colors separate these quasars from stars and normal galaxies. Spitzer's observations of high redshift quasars showed that their dust emission was already significant when the universe was young. Such findings indicate that dust production and enrichment occurred rapidly in the early universe, likely from supernovae and the winds of massive stars. Orientation plays a key role in how we perceive quasars. If we look directly into the accretion disk and broadline region, we see a Type 1 quasar with broad emission lines. If our line of sight grazes the torus, dust obscures the central region, and we see a Type 2 quasar with only narrow emission lines. The orientation also affects polarization and variability. For blazars, the jet is pointed nearly toward us, leading to rapid variability and strong polarization. Recognizing the influence of orientation helps unify diverse observations and reduces the need for separate categories. Broad absorption line BAL quasars challenge simple unification. Their spectra show deep absorption troughs from outflowing gas, often blue-shifted by tens of thousands of kilometers per second. BALs occur in about 10 to 20% of quasars. Some BALs, called LOBALs, exhibit absorption from low ionization species. FELOBALs show ion absorption. These features suggest that dense winds originate from the accretion disk or broadline region. Orientation may play a role in whether we see BALs, but intrinsic differences in wind strength may also be important. Studying BAL quasars sheds light on how quasars expel matter and influence their surroundings. Quasar host galaxies reveal a range of properties. At moderate redshifts, many quasar hosts are massive ellipticals, supporting the idea that mergers and interactions trigger quasar activity. Some radio-quiet quasars reside in spiral galaxies, showing that quasar activity can occur in diverse hosts. Deep imaging with the Hubble Space Telescope resolves the hosts and reveals structures like bars, rings, and tidal features. These observations show that quasar activity often coincides with disturbed morphologies, hinting at recent gravitational interactions. By studying host galaxies, we learn about the conditions that lead to black hole growth and quasar ignition. Star formation in quasar hosts can be either enhanced or suppressed by the quasar. In some systems, bursts of star formation accompany quasar activity, perhaps triggered by the same merger that fuels the black hole. In other systems, quasar winds and radiation heat or expel gas, reducing star formation. Determining which effect dominates requires measuring star formation rates and gas content in quasar hosts at different stages. Surveys combining infrared, optical, and radio observations reveal a complex interplay between quasar power and star formation, with outcomes that depend on environment and timing. The cosmic timeline traced by quasars is a narrative of growth and decline. Quasar activity rises sharply as galaxies assemble and merge, reaching a peak when the universe is a few billion years old. During this epoch, the black holes grow rapidly and quasars are common. As galaxies age and gas supplies diminish, quasar activity wanes. Today, most galaxies harbor dormant black holes with only a trickle of accretion. A few active galaxies and low luminosity AGN carry on the tradition, providing a present-day laboratory for studying processes that once dominated the universe. Gravitational waves have opened a new frontier for quasar research. While individual quasars do not emit detectable gravitational waves, merging supermassive black holes in quasar remnants might. Pulsar timing arrays seek to detect a background of low-frequency gravitational waves produced by such mergers. Future space-based observatories like LISA will directly detect gravitational waves from merging massive black holes at cosmological distances. Observing these mergers will complement electromagnetic studies by revealing the population of black hole binaries and their growth history. Multi-messenger astronomy, combining electromagnetic, gravitational wave, and neutrino observations, promises to revolutionize our understanding of quasars and their environments. For example, if a blazar emits neutrinos along with gamma rays, it could help identify the sources of ultra-high energy cosmic rays. Coordinated campaigns across observatories will allow researchers to track flares, jets, and accretion processes in real time. Quasars thus stand at the intersection of several branches of physics, making them fertile ground for interdisciplinary research. Discovering quasars at higher redshift continues to push the limits of technology. Wide-field surveys search for extremely red objects that might be high-Z quasars. Spectroscopic confirmation requires large telescopes and sensitive instruments. Each new high-Z quasar discovered adds to our understanding of the early universe. The challenge is to find them among the vast number of faint, red sources in survey data. Machine learning algorithms now sift through catalogues to identify promising candidates, demonstrating how computational techniques accelerate discovery. Quasars help probe reionization by illuminating the end of the cosmic dark ages. The Gunn-Peterson trough, a deep absorption feature in the spectra of Z greater than 6 quasars, indicates a high fraction of neutral hydrogen. The disappearance of this trough at slightly lower redshift signals the completion of reionization. By comparing the spectra of multiple high Z quasars, astronomers chart the progression of reionization across the universe. The patchiness of reionization may be probed by differences between sightlines, revealing how ionized bubbles grew and overlapped. The measurement of the Hubble constant using lensed quasars is an example of time delay cosmography. Light from a quasar splits into multiple images as it passes around a massive foreground galaxy. Variations in the quasar's brightness appear in each image at different times due to the different paths and gravitational potentials. Measuring these time delays, combined with models of the lensing galaxy's mass distribution, yields the absolute scale of the universe. Such measurements complement those from Cepheids and supernovae, offering an independent route to one of cosmology's key numbers. Cosmic time dilation, predicted by relativity, can be tested with quasar variability. If the universe is expanding, the intrinsic timescales of distant objects should appear stretched by a factor of 1 plus z. Studies of quasar light curves show evidence for this effect, with high redshift quasars varying more slowly in our frame. Confirming time dilation provides yet another validation of the cosmological framework. It also serves as a reminder that our perceptions of time and change are intimately tied to the geometry of the cosmos. Microlensing of quasars occurs when stars in a lensing galaxy pass in front of a lensed quasar image, causing its brightness to fluctuate. Microlensing allows astronomers to probe the structure of the quasar's accretion disk on very small scales. Different wavelengths are microlensed to different extents, revealing the temperature gradient in the disk. Microlensing can also uncover substructure in the lensing galaxy's dark matter halo. Such detailed studies exemplify the richness of phenomena that quasars enable, turning them into tools for investigating both their own structure and that of the intervening universe. The microphysics of accretion disks remains an active research area. Viscous processes allow angular momentum to be transported outward, enabling gas to spiral inward. Magnetic turbulence, described by the magnetorotational instability, drives this transport. Radiative processes determine how energy is emitted and whether the disk is thin and cool or thick and hot. Simulations of accretion flows, incorporating relativity and magnetohydrodynamics, reveal complex structures like spiral density waves and magnetically launched winds. Understanding these processes is essential to explain how quasars convert gravitational energy into the light we see. The launch of jets involves magnetic fields threading the accretion disk and black hole. The Blandford-Znajek process extracts energy from a spinning black hole via magnetic field lines anchored in the ergosphere. The Blandford-Payne mechanism launches winds from the disk's surface. In both cases, rotation and magnetism work together to accelerate plasma to relativistic speeds. Observations of polarized light from jets confirm the presence of ordered magnetic fields. Very long baseline interferometry images resolve jets on millisecond scales, showing the formation and collimation zones close to the black hole. Black hole spin is a parameter of growing interest. A rapidly spinning black hole can have an ergosphere where frame dragging occurs. Spin affects the efficiency of accretion and the strength of jets. Measuring spin requires interpreting the shape of spectral lines, like the FEK alpha line and the continuum emission. Some quasars seem to host highly spinning black holes, while others spin more slowly. Spin may result from the history of mergers and accretion. Determining how spins are distributed will help reveal the evolutionary paths of supermassive black holes. Despite decades of progress, many mysteries remain. We still do not fully understand how the first black holes formed, or how jets sustain their collimation over hundreds of thousands of light years. The role of magnetic fields in accretion disks, the origin of variability patterns, and the interplay between black holes and galaxies continue to challenge theorists. Future telescopes, both on the ground and in space, will bring sharper images, broader spectra, and deeper surveys. As our tools improve, so will our ability to unravel the complexities of quasars and their place in the cosmos. Throughout this journey, our perspective has shifted from seeing quasars as anomalies to recognizing them as fundamental components of cosmic evolution. The once puzzling radio sparks have become well-studied laboratories for physics and cosmology. Yet each answer uncovers new questions, inviting us to look deeper and to think more broadly. Our exploration of quasars reflects the human desire to understand the universe, to trace its history, and to find our place within it. As we continue, we carry forward a sense of wonder and a commitment to curiosity. Quasars reside within galaxies, and those galaxies inhabit larger structures. Studies of quasar environments reveal that luminous quasars tend to avoid the densest galaxy clusters, but are more common in moderately rich groups. This suggests that interactions in group environments may trigger quasar activity by funneling gas inward, while the hot gas in rich clusters suppresses accretion. Measurements of the clustering of quasars relative to galaxies show that quasars inhabit dark matter halos with masses around 1 trillion suns. These environmental clues help us understand how large-scale structure influences black hole growth. Jets not only carry energy away from quasars, but sometimes trigger star formation. When a relativistic jet plows into the interstellar medium, it compresses gas and can induce the collapse of molecular clouds. Observations of radio galaxies show strings of young star clusters aligned with jets, evidence of jet-induced star formation. This positive feedback contrasts with the more commonly discussed quenching of star formation by quasar winds. Understanding when and where jets stimulate or suppress star formation provides a nuanced view of how quasars influence their hosts. Quasar feedback occurs in different modes. In quasar mode, radiatively efficient accretion produces strong winds that can drive gas out of the galaxy. In radio mode, low luminosity accretion powers jets that heat the surrounding gas. Radio mode feedback is thought to regulate cooling flows in galaxy clusters, preventing gas from condensing and forming stars. Quasar mode feedback may occur during brief but intense accretion episodes. Observations of cavities in hot X-ray gas around radio galaxies attest to the heating power of jets. These modes represent different phases in the life of a black hole and its host galaxy. Evidence for cosmic downsizing comes from the observation that the most massive black holes formed early and then became quiescent, while lower mass black holes continue to grow at later times. The space density of luminous quasars peaks at redshift 2 and declines thereafter. Meanwhile, low luminosity active galactic nuclei remain relatively common at low redshift. This pattern mirrors the downsizing observed in star formation, where massive galaxies form their stars early and smaller galaxies form later. The parallel suggests a link between black hole growth and star formation histories across cosmic time. Quasars contribute to the cosmic energy budget in several wavelengths. The cosmic X-ray background arises in part from the integrated emission of obscured and unobscured active galactic nuclei. The cosmic infrared background includes contributions from dust-enshrouded quasars re-radiating absorbed ultraviolet light. By modeling the spectral energy distributions of quasars and their abundance over time, astronomers estimate their contribution to these backgrounds. These calculations connect the growth of black holes to the diffuse glow that permeates the universe, linking small-scale engines to large-scale backgrounds. Orientation not only affects classification, but also influences observed variability. When we look down a jet, relativistic beaming amplifies emission and shortens variability timescales. For sources viewed at larger angles, variability appears slower and less dramatic. Polarization measurements reveal the orientation of magnetic fields in jets and accretion disks. High polarization often accompanies blazars, reflecting synchrotron emission from ordered fields. Lower polarization in radio-quiet quasars suggests a more isotropic radiation field. Passing these orientation effects helps disentangle intrinsic variations from geometric factors. The winds launched from quasars enrich the intergalactic medium with heavy elements. The broad absorption lines trace gas containing carbon, nitrogen, and silicon. Over cosmic time, repeated outflows distribute metals into the circumgalactic and intergalactic medium. Observations of metal absorption lines at various redshifts show that the universe was enriched early, indicating that quasars and galaxies quickly processed gas into heavier elements. Studying the chemical evolution of the intergalactic medium via quasar absorption lines thus informs theories of nucleosynthesis and galaxy evolution. Galactic mergers play a crucial role in triggering quasar activity. Simulations show that when two galaxies collide, tidal forces funnel gas toward the center, feeding the black hole. The intense gravitational interaction may also disrupt the orbits of stars and gas, creating tidal tails and shells. Observations of quasar-host galaxies frequently reveal disturbed morphologies and close companions. Major mergers involving comparable mass galaxies can ignite luminous quasars, while minor mergers may fuel lower luminosity activity. Understanding the merger history of quasar hosts helps connect black hole growth to galaxy assembly. Dust plays both a concealing and a revealing role in quasar studies. Dust grains absorb ultraviolet and optical light and emit in the infrared. In some quasars, dust obscures the central engine, making them appear red in optical surveys. These reddened quasars were once underrepresented, but infrared selection has uncovered many more. Dust also polarizes light through scattering, yielding clues to the geometry of the scattering region. By modeling dust absorption and emission, astronomers estimate the amount of obscuration and correct for selection effects in quasar surveys. Contemplating cosmic timescales reveals the fleeting nature of human experience. A quasar flare that lasts a month corresponds to a few days in its rest frame at Z equals 2. The billions of years light travels to reach us dwarf the entire history of human civilization. Yet through science, we can reconstruct events from epochs beyond imagination. Thinking about quasar light crossing the expanding universe invites reflection on the interconnectedness of time and space. Each photon tells a story that began long before Earth formed, now arriving just as we have the tools to decode it. Machine learning has become an invaluable tool in quasar research. Algorithms trained on known quasars can sift through vast photometric catalogues to find new candidates. Neural networks classify spectra, identify emission lines, and flag anomalies that may represent rare or interesting objects. Unsupervised clustering reveals patterns and subpopulations within quasar samples. As datasets grow, machine learning helps astronomers handle the deluge of data, enabling discoveries that would be impossible by manual inspection alone. The synergy between computational techniques and human insight accelerates the pace of exploration. Citizen science engages the public in quasar discovery. Projects like Galaxy Zoo and its spin-offs invite volunteers to classify galaxies, quasars, and transient events. Participants have helped identify unusual quasar hosts, gravitational lenses, and changing-look quasars. Citizen scientists bring the power of collective human pattern recognition to bear on complex datasets. Their contributions democratize science and foster a sense of shared curiosity. In a field as vast as quasar research, the help of many eyes expands our ability to explore. Open data policies have transformed astrophysics. Surveys like SDSS release their images, spectra, and catalogues to the world. Researchers anywhere can access and analyze these data, leading to discoveries not envisioned by the original teams. The accessibility of quasar catalogues allows students to conduct research projects and professional astronomers to test new hypotheses. Open data fuels collaboration across institutions and disciplines, making quasar research a truly global enterprise. Gravitational lensing studies continue to advance. New telescopes with higher resolution and deeper sensitivity find more lensed quasars. Modeling the lensing galaxy's mass distributions has become more sophisticated, incorporating dark matter halos and baryonic structures. Time delay measurements refine the Hubble constant. Some lensed quasars exhibit microlensing variations that reveal the size of the accretion disk in multiple wavelengths. These techniques offer glimpses into structures far too small to resolve directly, demonstrating the power of natural cosmic lenses. Neutrino astronomy adds another dimension to quasar studies. In 2018, a high-energy neutrino detected by IceCube was traced back to a flaring blazar. This association suggested that some blazars accelerate protons that interact to produce neutrinos and gamma rays. Although the link is still tentative, it opens the possibility that quasars contribute to the flux of cosmic neutrinos. Future multi-messenger observations could confirm these sources and shed light on particle acceleration in jets. Such connections bridge astrophysics and particle physics. Extragalactic cosmic rays may also originate in quasar jets. The highest energy cosmic rays must come from outside our galaxy. Jets from active galaxies are capable of accelerating protons and nuclei to ultra-high energies. If these particles escape the host galaxy, they could contribute to the cosmic ray flux detected on Earth. Determining the sources of ultra-high energy cosmic rays remains a challenge, but quasars are among the prime candidates. Studies of jet composition and magnetic fields aim to evaluate this possibility. Orientation-based classifications continue to evolve. Some quasars show properties that do not fit neatly into existing categories. Changing look quasars switch between showing broad and narrow lines, perhaps due to variations in accretion rate or obscuration. Some objects display properties of both radio loud and radio quiet quasars. These cases remind us that nature is complex and that our classifications are approximations. They encourage us to refine models and to remain open to surprises. Collaborations between gamma-ray and neutrino observatories, such as Fermi and IceCube, increase the chances of identifying cosmic accelerators. When both a gamma-ray flare and a neutrino are detected from the same direction, it strengthens the case for a common source. Such events can test models of particle acceleration and jet composition. Coordinated monitoring across the electromagnetic spectrum, along with neutrino and gravitational wave detectors, heralds a new era of quasar studies, where multiple messengers paint a more complete picture. As we near the end of this section, we appreciate how far quasar research has come since the days of crude radio maps. The journey has been one of expanding horizons, both literally and figuratively. From the early identification of mysterious points of light to the construction of a unified model encompassing a vast array of phenomena, the study of quasars exemplifies the power of curiosity and collaboration. In the chapters to come, we will delve deeper into the physical processes at work in these cosmic beacons, exploring the mechanics of accretion, the origin of jets, and the role of quasars in shaping the universe. For now, we pause to reflect on the path traveled and the mysteries that still beckon us forward. The next generation of telescopes promises to revolutionize quasar astronomy. The James Webb Space Telescope, with its sensitivity to infrared light, will observe high redshift quasars whose light has been stretched into the infrared by cosmic expansion. JWST's ability to dissect quasar host galaxies at early times will illuminate the interplay between star formation and black hole growth during the first billion years. Its spectroscopy will reveal chemical abundances and dust properties in these distant objects. By peering into the epoch of reionization, JWST will push our understanding of quasars to new depths and challenge current models. Other planned missions, such as Euclid and the Nancy Grace Roman Space Telescope, will map the distribution of galaxies and quasars to study dark energy and cosmic acceleration. Euclid's wide-field imaging and spectroscopy will catalogue millions of galaxies and hundreds of thousands of quasars across vast volumes. By measuring baryon acoustic oscillations and weak gravitational lensing, these missions will provide independent probes of cosmology. Quasars within their fields will serve as backlights for studying the intergalactic medium and as markers of large-scale structure. The synergy between dark energy missions and quasar science exemplifies the interconnected nature of modern astronomy. The Vera C. Rubin Observatory's legacy, Survey of Space and Time, LSST, will deliver an unprecedented movie of the sky. By imaging the entire visible sky every few nights for a decade, LSST will capture the variability of hundreds of thousands of quasars. It will identify transients, such as tidal disruption events when stars are torn apart by black holes, and track changing-look quasars. LSST's data volume will require advanced algorithms and community cooperation. The time domain emphasis will enrich our understanding of quasar variability, fueling models of accretion and providing targets for follow-up by larger telescopes. Among quasars themselves, some stand out as hyperluminous. These extreme objects radiate more than 1,000 times the luminosity of typical quasars. Some may be accreting at rates exceeding the Eddington limit, perhaps due to special conditions in their hosts. Hyperluminous quasars serve as laboratories for testing accretion physics under extreme conditions. Their immense brightness also makes them detectable across enormous distances, making them powerful probes of the distant universe. Studying these outliers helps constrain the upper limits of black hole growth and the conditions necessary for such prodigious energy output. On the largest scales, quasars trace structures of surprising size. Surveys have found quasar groups stretching over 1 billion light-years, sometimes called large quasar groups or superclusters. These structures challenge our understanding of cosmic homogeneity and test models of structure formation. By mapping quasar clustering, astronomers infer the bias of quasar hosts relative to the underlying dark matter distribution. Large quasar structures may represent the most massive overdensities in the early universe, offering a window onto the formation of galaxy clusters and the growth of cosmic structure. Quasar absorption lines not only map the cosmic web, but also measure cosmological parameters. Baryon acoustic oscillations, imprinted on the distribution of matter by sound waves in the early universe, leave a characteristic scale in the clustering of galaxies and quasars. By analyzing the Lyman alpha forest in quasar spectra, researchers measure this scale at high redshift. The resulting constraints on the expansion history complement those from galaxy surveys at lower redshift. The combination of quasar absorption data and galaxy clustering data tightens cosmological models, demonstrating the power of multi-tracer analyses. As we close this first part of our exploration, we look ahead to deeper inquiries into the heart of quasar engines. We will journey inward to the accretion disk and examine the forces that shape it. We will follow particles as they spiral into oblivion and emerge as jets, carrying energy back into the universe. We will consider the dance of matter and radiation, of gravity and magnetism. The questions posed by quasars lead naturally to broader themes about the nature of space, time, and energy. This is not an ending, but a transition. A pause before we descend further into the mechanics of cosmic beacons and their role in the unfolding drama of the cosmos. Despite the progress made, fundamental mysteries remain. We still do not know how the first black holes formed, or how they grew so massive so quickly. The details of accretion at extreme rates, the origins of magnetic fields that launch jets, and the reasons why some quasars are radio loud, while most are radio quiet, all continue to puzzle researchers. The interplay between quasar feedback and galaxy formation raises questions about the coevolution of black holes and their hosts. These open problems motivate the next generation of observations and simulations, promising new insights as the field advances. Our fascination with quasars goes beyond their scientific importance. They stir the imagination because they are both remote and intimately connected to cosmic history. The photons we capture began their journey when the universe was young, yet they interact with our detectors here and now. Thinking about quasars invites us to contemplate scales of time and space far beyond everyday experience. They remind us that the universe is vast and filled with wonders yet to be understood. As we continue this journey, we carry the quiet thrill that comes from peering into the depths of time and space, guided by the light of distant quasars. As telescopes improved, surveys broadened the census of quasars and other active nuclei. The 3C and 4C catalogues were only the beginning. In the late 1990s, the 2DF Quasar Redshift Survey used the Anglo-Australian telescope to obtain redshifts for over 20,000 quasars. This survey mapped their distribution across the sky and provided one of the first large samples for statistical analysis. The 2DF sample showed that quasars were more common at earlier cosmic times and that their numbers peaked around 10 billion years ago. It also revealed large-scale structures traced by quasars, hinting at the cosmic web. Building on the success of 2DF, the 2SLAQ survey employed the 2-degree field instrument to target fainter quasars. Over several semesters, it gathered redshifts for more than 5,000 quasars across about 100 square degrees. Its goal was to extend the quasar luminosity function to fainter levels and to test models of black hole growth. The early results from 2SLAQ suggested a steeper increase in the number of faint quasars than expected, implying that many low luminosity quasars were still waiting to be discovered. Such efforts illustrated the rapid progress in assembling quasar catalogues. The Sloan Digital Sky Survey, SDSS, ushered in a new era of sky mapping. Using a dedicated telescope and multi-fiber spectrographs, SDSS produced multicolour images covering over a quarter of the sky and created three-dimensional maps containing hundreds of thousands of galaxies and quasars. The Baryon Oscillation Spectroscopic Survey, a component of SDSS, obtained spectra for more than 500,000 galaxies and over 100,000 quasars up to redshift 3 SDSS quasar samples are hundreds of times larger than those of earlier surveys, enabling detailed studies of quasar demographics and evolution. SDSS not only increased the number of known quasars, but also provided high-quality spectra. For example, researchers combined spectra of tens of thousands of quasars to derive a composite spectrum, revealing subtle features otherwise lost in individual observations. Such composite studies helped refine models of the broad emission line region and the accretion disk continuum. With so many objects, astronomers could examine how quasar properties depend on redshift, luminosity, and environment. SDSS also discovered new classes of quasars, such as those with unusual dust reddening or extreme accretion rates. Parallel to SDSS, other surveys extended the census of active nuclei across the electromagnetic spectrum. Radio interferometers mapped jets in detail. X-ray observatories measured high-energy emission. Infrared telescopes penetrated dusty regions to find hidden quasars. Together, these programs painted a richer picture of the active universe. By studying quasars across wavelengths, astronomers identified correlations between radioluminosity, X-ray emission, and optical properties. They learned that the engine emits across the spectrum, with different components dominating at different energies, from the hot corona to the cool, dusty torus. The golden age of surveys transformed quasars from rare curiosities into abundant data points. Instead of a handful of objects, astronomers now had tens of thousands to analyze. This statistical power allowed them to calculate luminosity functions, measure quasar clustering, and test models of cosmic evolution. Quasars became tools for studying the universe itself, serving as probes of intergalactic gas and cosmic expansion. Their bright light shines through intervening gas, leaving absorption features that trace the distribution of matter across cosmic time. While surveys answered many questions, they also raised new ones. One puzzle concerns how supermassive black holes form and grow so quickly. Quasars with redshift greater than 6 existed when the universe was less than 1 billion years old. To reach masses of 1 billion solar masses by that time requires rapid accretion or mergers. Observers search for seeds of these black holes in the first galaxies and look for signs of massive star clusters collapsing. The interplay between black hole growth and galaxy formation remains a central theme of modern astrophysics. Another question involves the role of feedback. Quasar winds and jets can inject enormous energy into their host galaxies and the surrounding intergalactic medium. Feedback may regulate star formation by heating gas and preventing it from cooling. At the same time, outflows may trigger star formation in some regions by compressing gas. Understanding feedback requires connecting small-scale processes near the black hole to large-scale galactic dynamics. The signatures of feedback can be seen in the spectra of quasar hosts, the kinematics of surrounding gas, and the temperature of the circumgalactic medium. Quasars also serve as signposts for mapping the cosmic web. Because they are bright and numerous, they can be used to trace large-scale structure across billions of light-years. The distribution of quasars on the sky reveals the clustering of dark matter halos and the growth of cosmic structure over time. By analyzing the spatial correlations of quasars and galaxies, astronomers test cosmological models and measure parameters, such as the matter density and the amplitude of density fluctuations. These studies link the small, intense processes near a black hole to the grand architecture of the universe. In addition to their scientific value, quasars inspire wonder. They represent some of the most luminous and distant objects we can see. Observing a quasar is like peering back in time to an era when the universe was young and galaxies were still forming. The fact that light from these objects travels billions of years to reach us invites contemplation about cosmic timescales and the transient nature of human existence. Quasars remind us of the vastness of the cosmos and our tiny place within it. As the first part of our journey draws to a close, we have followed the evolution of ideas and observations that led from puzzling radio sparks to a rich tapestry of active galaxies. We have seen how careful measurements, patient analysis, and imaginative leaps turned mysterious points of light into powerful tools for exploring the universe. Yet the story is far from finished. In the chapters ahead, we will delve deeper into the engines that power quasars, the physics of accretion and jets, and the role of quasars in cosmic evolution. The gentle light of these ancient beacons continues to guide our curiosity, illuminating mysteries yet to be explored. Continuing our exploration of quasars, we now journey into the dark heart at the center of each beacon. In the depths of these cosmic lighthouses lies a supermassive black hole, a region where the gravitational pull is so intense that not even light can escape. These titans weigh millions to billions of times the mass of our Sun, yet they remain hidden behind a cloak of darkness. Around them, matter falls inward, releasing vast amounts of energy as it spirals ever closer to the event horizon. The darkness itself seems to glow with borrowed radiance, a paradox that invites deeper contemplation. The gravitational potential energy that fuels a quasar is unimaginably vast. As gas and dust drift toward the central hole, they lose orbital energy and convert it into heat and light. Each particle sacrifices a portion of its mass to the gravitational embrace, and the resulting radiation floods out across the universe. In this way, the quasar becomes a cosmic engine, powered not by nuclear fusion, but by the inexorable pull of gravity. The process is both efficient and relentless, transforming infalling matter into torrents of photons. Imagine peering across cosmic distances and witnessing a storm of gas swirling around an invisible core. The material rushes inward in ever tighter orbits, heating to millions of degrees as friction and compression do their work. At such temperatures, atoms are stripped of their electrons, and the resulting plasma glows across a broad range of wavelengths. The black hole itself remains silent and dark, but the surrounding maelstrom blazes with a brilliance that can outshine an entire galaxy. The sheer scale of this transformation defies ordinary experience, evoking awe and humility. At the heart of a quasar, the supermassive black hole anchors the entire system. Its immense mass curves spacetime so strongly that paths of light bend inward, and time itself slows in its vicinity. Observers far away see the clock near the horizon ticking ever more slowly, as if the infalling matter were moving through treacle. Yet for particles plunging inward, time passes normally until the final moments of their journey. This strange interplay between perspectives reminds us that gravity distorts more than just trajectories. It alters the very fabric through which events unfold. The black hole's event horizon marks a point of no return, but its influence extends far beyond this boundary. Surrounding the horizon is a region where particles orbit at speeds approaching that of light. These tight orbits amplify the effects of general relativity, causing precession and twisting of space. The rotation of the black hole drags space-time with it, an effect known as frame dragging. Through these subtle mechanisms, the central mass can communicate its spin to the surrounding flow, creating an intimate connection between the whole and its luminous environment. Even without direct interaction, the geometry of space-time weaves the threads of cause and effect. Material that ventures too close to the central hole experiences tidal forces that tear it apart. Stars wandering into this region can be shredded, their constituent gas strewn across the accretion disk. Clouds of gas are sheared and heated, emitting intense radiation as they are consumed. The violence of this process belies the serene glow we see from afar. Each photon that escapes carries with it the memory of matter's final moments, encoded in its energy and its direction. By studying these emissions, astronomers decode the story of how matter meets its end in the jaws of gravity. Though they bear the moniker black, these holes are anything but empty. They are the collapsed remnants of massive stars, or the result of countless mergers within galactic nuclei. Over cosmic time, they swallow ever more material, growing from tens of solar masses to millions or billions. The environment around them reflects their growth. Dense star clusters, gas clouds, and dusty rings all swirl within the gravitational well. Occasionally, a passing galaxy will provide a fresh supply of fuel, awakening a dormant nucleus and igniting a quasar. The cycle of feeding and quiescence gives rise to the cosmic diversity we observe. Supermassive black holes do not exist in isolation. They are part of the galaxies they inhabit. Their masses correlate with the properties of their host bulges, hinting at a symbiotic evolution. As the black hole grows, it can influence star formation by injecting energy and momentum into the surrounding gas. The luminous phases we call quasars may blow out gas from the galaxy, regulating future growth. In this way, the dark heart at the center has a profound effect on the visible structure around it. The interplay between small-scale gravity and large-scale dynamics is a theme we will encounter again and again. The interplay between gravity and angular momentum sets the stage for everything that follows. Without angular momentum, gas would fall straight into the hole and disappear. Instead, conservation of angular momentum forces the material into a rotating disk, where viscosity redistributes the orbital energy outward and mass inward. The details of this disk and its physics will occupy much of our attention, for it is there that the quasar's light is actually generated. The black hole may be dark, but its influence shapes the flow of matter and energy in ways we can observe across billions of light years. Having glimpsed the dark heart, we now turn our attention to the swirling disks of gas that melt the night. These structures, delicate yet powerful, convert gravitational potential into heat and radiation with astonishing efficiency. By understanding their behavior, we can begin to decode the light we observe, and in doing so, trace the secret lives of supermassive black holes. The journey from darkness to brilliance begins on the slender plane of the accretion disk, where atoms dance and collide on their way toward oblivion. Let us linger there for a while and listen to their quiet whispers. The accretion disk forms when gas is captured by the black hole's gravity, but cannot fall straight in due to its angular momentum. Instead, the gas settles into a flattened, rotating structure, like a cosmic whirlpool seen from above. Each ring of gas moves at nearly the Keplerian speed appropriate for its distance from the center. As neighboring rings rub against each other, friction converts some of their orbital energy into heat. This thermal energy then escapes as radiation, cooling the gas and allowing it to sink closer to the black hole. The process repeats, drawing the material inexorably inward. The physics of viscosity plays a crucial role in accretion. In everyday fluids, Viscosity arises from molecular interactions, but in a plasma swirling around a black hole, the viscosity is dominated by turbulence and magnetic forces. Magnetic fields thread through the disk and couple different layers of gas, allowing angular momentum to be transported outward. As a result, gas in the inner regions loses angular momentum and spirals inward, while gas in the outer disk gains angular momentum and moves outward. Without this transport, the disk would remain static, and the black hole would never grow. The delicate balance of forces within the disk is what sustains the luminous flow. Thin disks occur when the accretion rate is moderate, and the cooling time is shorter than the dynamical time. In this regime, the disk remains geometrically thin, with its height much smaller than its radius. The gas moves in nearly circular orbits, and the heat generated by friction is radiated away efficiently. Such a disk emits a spectrum that peaks in the ultraviolet or soft X-ray region, corresponding to temperatures of tens of thousands to a few 100,000 Kelvin. Observing these disks allows astronomers to infer the properties of the black hole, including its mass and the rate at which it is accreting material. When the inflow of gas becomes extremely high, the disk enters a different regime. Radiation pressure can exceed the pull of gravity on electrons, creating a limit known as the Eddington luminosity. At this threshold, the outward pressure of photons balances the inward pull on charged particles. If the accretion rate surpasses this limit, the disk thickens and becomes unstable, developing funnels that channel radiation and matter. Such slim disks can radiate more energy than would be expected based on the Eddington limit because the radiation escapes preferentially along the poles. These super Eddington flows may power some of the most luminous quasars observed. At the other extreme, when the accretion rate is low, the disk can become hot and geometrically thick. In this case, cooling is inefficient, and much of the heat is carried inward with the gas. The resulting structure is known as an advection-dominated accretion flow. Instead of radiating efficiently, the gas retains its energy until it plunges into the black hole. Such flows are dimmer, but hotter, emitting primarily in hard X-rays. They may play a role in low-luminosity active galactic nuclei, where the central engine is quietly simmering rather than blazing. Regardless of the regime, the accretion disk is the furnace that melts the night. Its radiation bathes the surrounding environment, providing the seed photons that will be upscattered into higher energies by a hot corona above the disk. The disk also feeds the magnetic fields that connect to the black hole and launch outflows. Its structure and stability are therefore central to our understanding of how quasars shine. By studying the emission from disks across the electromagnetic spectrum, we learn about viscosity, turbulence, and the fundamental physics of plasmas under extreme conditions. Viscosity within the disk is not due to sticky fluid, but rather to the collective behavior of particles and fields. Turbulence arises when magnetized plasma becomes unstable to the magnetorotational instability. This instability allows small perturbations in the magnetic field to grow, driving chaotic motions that enhance angular momentum transport. In this sense, magnetic fields are both the glue and the stirrer, organizing the plasma on large scales while promoting disorder on small scales. The interplay between order and chaos within the disk sets the stage for phenomena that occur further out, including winds and jets. One of the remarkable features of accretion disks is their ability to maintain a steady temperature gradient. The inner regions are hotter and radiate at shorter wavelengths, while the outer regions are cooler and emit in the infrared. As you move outward along the disk, the color of the emitted light changes gradually, creating a continuous spectrum that reveals the temperature distribution. Embedded within this smooth gradient are subtle variations caused by instabilities, magnetic turbulence, and changes in accretion rate. These variations can lead to flickering and flares, which we will explore when we discuss variability. The disk is not a static structure. It evolves as gas flows inward. Over timescales of thousands to millions of years, the disk can change thickness, composition, and luminosity. Episodes of enhanced accretion can brighten the quasar dramatically, while periods of quiescence can dim it. The feeding of the disk is influenced by processes occurring on galactic scales, such as galaxy mergers and tidal interactions. Thus, the story of the disk is intertwined with the history of its host galaxy. Understanding this connection requires bridging scales from light hours to hundreds of thousands of light years, a challenge that has inspired generations of astronomers. With a picture of the disk in mind, we can now turn to the enigmatic corona that hovers above it. This hot, tenuous plasma plays a crucial role in shaping the high-energy spectrum of quasars. Through interactions with the disk's photons, the corona generates X-rays that pierce the surrounding gas and dust. These rays serve as both a diagnostic of the inner regions and a source of energy for reprocessing material. The mysteries of the corona are intertwined with the mysteries of the black hole's magnetic environment, and together they create a web of phenomena that extend far beyond the disk itself. Above the luminous disk lies a region of hot, diffuse gas known as the corona. This halo of plasma is energized by magnetic reconnection and turbulent motions, reaching temperatures of hundreds of millions of degrees. At such high temperatures, electrons move at relativistic speeds and can impart significant energy to the photons they encounter. When a low-energy photon from the disk enters the corona, it may collide with an energetic electron and gain energy. This process, called inverse Compton scattering, boosts the photon into the X-ray band. In this way, the corona transforms the soft ultraviolet light from the disk into the hard X-rays that characterize many quasars. The spectrum produced by Compton scattering has a distinctive shape. It often appears as a power law distribution in which the intensity declines gradually with increasing energy. The slope of this power law is determined by the temperature and optical depth of the corona. A hotter corona produces harder, higher energy X-rays, while a denser corona yields a steeper spectrum. Observing the X-ray spectrum allows astronomers to infer properties of the corona that cannot be seen directly. This information, combined with spectral features from reflection, reveals the geometry and composition of the inner accretion flow. Not all photons escape directly after being upscattered. Many of them return toward the disk and interact with the dense material there. When high-energy X-rays strike the cooler disk, they can be absorbed by heavy elements and re-emitted at characteristic energies. One of the most prominent features produced in this way is the iron K-alpha line, a narrow emission line at around 6.4 kiloelectron volts. The shape and strength of this line carry information about the velocity and ionization state of the disk. Combined with the Compton hump created by scattered X-rays, these features form a reflection spectrum that complements the direct emission. The corona itself is not static. It may consist of magnetic flares, loops, or a continuous blanket of hot plasma. In some models, the corona forms a sandwich above and below the disk, while in others, it is concentrated in a compact region near the black hole. The geometry influences how efficiently photons are upscattered and how they illuminate the disk. Changes in the corona's structure can lead to variability in the X-ray emission, providing clues about the physical processes at work. By monitoring these variations, astronomers can study the timescales of heating and cooling in the corona. In addition to upscattering photons, The corona may also produce its own radiation through Bremsstrahlung and synchrotron processes. Electrons spiraling in magnetic fields emit synchrotron radiation, which can contribute to the low-energy end of the X-ray spectrum. When electrons are deflected by ions, they emit Bremsstrahlung radiation, adding further complexity to the observed spectrum. These processes interplay with Comptonization, creating a rich tapestry of emission that spans a wide range of energies. Deciphering this tapestry requires careful modeling and observations across multiple wavelengths. The X-ray emission from the corona is important, not only for what it tells us about the corona itself, but also for how it affects the surrounding environment. X-rays are energetic enough to ionize atoms and molecules in the disk and the torus. This ionization can alter the chemistry of the gas and influence how it absorbs and re-emits radiation. In some cases, X-ray heating can drive winds from the disk's surface, contributing to outflows that carry away mass and angular momentum. Thus, the corona plays a dual role as both a diagnostic and an actor in the quasar's evolution. Observing X-rays from distant quasars is challenging, but space-based telescopes have opened a window into this hidden regime. Each photon recorded by an X-ray detector carries information about the conditions near the black hole a few moments before it was emitted. By analyzing large populations of quasars, astronomers have discovered trends in the X-ray to optical flux ratio, the hardness of the X-ray spectrum, and the presence or absence of reflection features. These trends illuminate the diversity of coronae and hint at connections between the corona and the properties of the black hole and disk. Variability in the X-ray band reveals that the corona is a dynamic, turbulent environment. Rapid fluctuations on timescales of hours or less suggest that parts of the corona can brighten or dim quickly. Slower variations over days or weeks may correspond to larger scale changes in the disk or the magnetic field configuration. Occasionally, quasars exhibit dramatic flares in X-rays, hinting at sudden releases of energy in the corona. The timing and amplitude of these events provide insights into the size and structure of the emitting region. Such observations bring us closer to understanding the inner workings of these cosmic engines. As we contemplate the corona, it becomes clear that magnetic fields play an indispensable role. They thread through the disk and the corona, connecting distant regions and transporting energy. Through the process of magnetic reconnection, field lines can snap and reconnect, releasing energy that heats the plasma. In the presence of rotation, magnetic fields twist and wind, generating toroidal components that can drive outflows. To appreciate how these fields organize the quasar environment, we must delve into the tangled world of magnetism and its consequences. Magnetic fields within the disk originate from the motion of charged particles and are amplified by differential rotation. The magnetorotational instability acts as a dynamo, converting rotational energy into magnetic energy. Small seed fields can grow exponentially, threading the disk with loops and tangles. These fields exert tension that couples different layers of the disk, allowing angular momentum to be transported outward. At the same time, magnetic pressure can inflate the disk vertically, producing a thicker structure. The complex interplay between magnetic forces and gravity shapes the disk's appearance and behavior. Above the disk, magnetic fields can coalesce into coherent structures that rise into the corona. These structures may resemble loops and arches, reminiscent of solar prominences, but on a vastly larger scale. When two loops carrying opposite magnetic polarity encounter each other, they can reconnect, releasing stored magnetic energy as heat and accelerating particles. This reconnection is thought to be a key mechanism for heating the corona and sustaining its high temperature. The resulting bursts of energy may appear as flares in the X-ray light curve, revealing the transient nature of magnetic activity. Magnetic fields also mediate the exchange of angular momentum between the disk and the black hole. When field lines thread the event horizon, they link the rotating spacetime to the surrounding plasma. Through this connection, the spin of the black hole can be tapped, transferring rotational energy into electromagnetic energy. The process is subtle yet powerful. A twisting magnetic field extracts energy from the black hole and channels it into jets that shoot outward along the rotational axis. This extraction of spin energy is one of the most remarkable consequences of general relativity and magnetohydrodynamics. The collimation of jets depends critically on magnetic fields. As charged particles are accelerated outward, the fields guide them into narrow beams. The confinement arises because magnetic tension resists sideways expansion, while the pressure gradient drives the flow along the field lines. Further out, where the magnetic field weakens, the jets can expand and interact with the intergalactic medium. The structure of the field determines whether the jet remains coherent over thousands of light years or disperses more quickly. Observing the collimation and stability of jets provides clues about the underlying magnetic geometry. Variability in quasars often reflects changes in the magnetic field. Sudden enhancements in field strength or rearrangements of the field lines can trigger changes in the accretion flow and the corona. Magnetic turbulence within the disk can lead to quasi-periodic oscillations, while large-scale field reversals can drive long-term variability. The intimate relationship between magnetism and variability underscores the importance of understanding magnetic processes in accretion disks. By studying how the fields evolve over time, we gain insight into the dynamical nature of quasars. Jets launched from the vicinity of a black hole are among the most spectacular manifestations of magnetism at work. These streams of particles move at relativistic speeds, carrying away energy and momentum. Observed across the electromagnetic spectrum, jets can extend for hundreds of thousands of light years, connecting the central engine to the large-scale environment. The energy to power these jets is believed to come, at least in part, from the spin of the black hole itself. Through the process known as the Blandford-Znaeck mechanism, magnetic fields anchored in the disk and threading the black hole's event horizon extract rotational energy and launch it outward. The concept of extracting spin energy may seem counterintuitive. In a rotating black hole, space-time is dragged along with the rotation, creating an ergosphere outside the event horizon. Within this region, all particles must co-rotate with the black hole, but they can exchange energy in such a way that one particle falls into the hole with negative energy relative to infinity, while another escapes with extra energy. Magnetic fields facilitate this exchange on a grand scale. They act as a conduit, allowing energy and angular momentum to be transferred from the black hole to the outgoing jet. The result is a beam of relativistic plasma that can remain collimated over enormous distances. Jets are not simply featureless streams. They contain substructures such as knots and shocks. These features may arise when the jet interacts with clouds of gas in the host galaxy, or when internal instabilities develop. Shockwaves can accelerate particles to ultra-relativistic speeds, causing them to emit synchrotron radiation that glows in radio and X-ray wavelengths. Observations reveal that jets can also precess or wobble, possibly due to the influence of a companion black hole or misalignments between the disk and the black hole's spin axis. Each jet, therefore, carries the imprint of the central engine's dynamics and history. The apparent superluminal motion observed in some jets is a striking example of relativistic effects in astrophysics. when a jet is oriented close to our line of sight and moves at a speed near that of light. The time it takes for light from different parts of the jet to reach us can make the motion appear faster than light. This illusion arises not from any violation of the cosmic speed limit, but from the geometry of space and time. Superluminal motion tells us that jets are highly relativistic and provides a way to estimate their actual velocities and orientations. These measurements, in turn, help constrain models of jet launching and collimation. Jets have profound effects on their surroundings. As they plow through the interstellar and intergalactic medium, they heat and compress the gas, triggering or suppressing star formation. On galactic scales, jets can carve out cavities in the hot gas, visible as radiolobes. On larger scales, they deposit energy into galaxy clusters, offsetting cooling and influencing the evolution of the intracluster medium. Thus, the reach of a quasar's jet extends far beyond the immediate vicinity of the black hole, shaping the cosmic environment across many orders of magnitude in scale. Understanding jets requires a synthesis of general relativity, plasma physics, and radiation processes. Simulations of magnetically driven jets reveal complex structures, including helical fields, shocks, and shear layers. Observations at radio, optical, X-ray, and gamma-ray wavelengths provide complementary views of these structures. By comparing observations with theoretical models, researchers aim to uncover how jets are launched, how they remain collimated, and how they dissipate their energy. The study of jets thus serves as a bridge between the microphysics of black hole accretion and the macrophysics of galaxy evolution. Having explored the origin and behavior of jets, we turn to the regions where the quasar's light is filtered and reshaped before reaching us. The broad-line region and narrow-line region are two such zones, each characterized by distinct kinematic and physical conditions. The broad-line region lies close to the black hole, where gas moves at thousands of kilometers per second. The narrow-line region is farther out, with slower gas and lower density. Together, they produce the rich emission line spectra that allow astronomers to classify and study quasars. To understand what these lines reveal, we must take a closer look at the environment in which they are formed. In the broad-line region, clouds of gas orbit within light days to light weeks of the black hole. The intense radiation from the accretion disk ionizes these clouds, causing them to emit spectral lines when electrons recombine with ions. Because the gas moves so quickly, the lines are broadened by the Doppler effect, resulting in widths of thousands of kilometers per second. The density in this region is extremely high, allowing forbidden transitions to be suppressed and permitted transitions to dominate. The resulting spectrum is rich and complex, with lines of hydrogen, helium, carbon, and other elements overlapping and blending. The narrow line region lies farther from the black hole, extending across light years, or even tens of light years. Here, the gas density is much lower, and the velocities are in the hundreds of kilometers per second. Forbidden transitions are allowed, producing lines from ions such as O3, N2, and S2. These lines are narrower because the gas is moving more slowly, and they are less sensitive to short-term changes in the central source. The narrow line region often shows a conical shape, possibly due to illumination by a central source through an opening in the torus. The size and morphology of this region depend on the interaction between the central engine and the host galaxy. Between the broad and narrow line regions, there may be intermediate components or outflows. Some quasars exhibit broad absorption lines that indicate winds moving away from the central region at thousands of kilometers per second. These winds can carry significant amounts of mass and energy, potentially influencing the host galaxy. The presence of such outflows hints at a complex, multi-phase medium with regions of different density ionization, and motion. Understanding the structure and dynamics of these regions helps us interpret the spectra and physical conditions of quasars. The variability of emission lines provides additional information. When the continuum emission from the accretion disk changes, the broadline region responds with a delay corresponding to the light travel time. By measuring these delays, astronomers can estimate the size of the broadline region. The narrowline region, being larger, responds on much longer timescales and is often considered static for practical purposes. The contrast between the fast response of the broad lines and the slow response of the narrow lines underlies the technique known as reverberation mapping, which we will discuss in greater detail later. Detailed modeling of emission line spectra reveals the physical conditions within these regions. Line ratios can be used to determine electron density, temperature, and ionization state. The widths and profiles of the lines reveal the velocity distribution of the gas and hint at the geometry of the emitting region. For example, symmetrical profiles may suggest isotropic motions, while asymmetric profiles can indicate inflows, outflows, or disk-like structures. By combining spectroscopy with variability studies, astronomers can reconstruct a three-dimensional picture of the gas around the black hole. The broadline region is not uniform. It may consist of numerous clouds or streams of gas moving independently. These structures could be orbiting within a flattened configuration, forming a disk-like structure, or they could be part of a more spherical distribution. Some models propose that radiation pressure drives clumps of gas away from the disk, forming a fountain of material that rains back down. Others suggest that magnetic fields guide the flow into spiral arms or filaments. The true structure is likely complex and dynamic, changing as the accretion rate and radiation field evolve. The narrow line region often extends into the host galaxy, interacting with star-forming regions and the interstellar medium. Its size allows it to be resolved by telescopes, revealing intricate structures such as ionization cones, filaments, and bubbles. Observations show that the narrow line gas can be shaped by the jets and winds from the central engine, creating shock fronts and cavities. By studying the morphology of the narrow line region, astronomers can trace the impact of the quasar on its host and identify signatures of feedback. In this way, the narrow line region acts as both a diagnostic and a witness to the quasar's influence. With the emission line regions in mind, we now consider how orientation affects what we see. Not all quasars look the same, and much of this diversity can be explained by the presence of dusty structures that obscure our view at certain angles. Imagine a torus of gas and dust encircling the disk and broadline region. If we view the quasar face on, we see through the opening in the torus to the bright central region. If we view it edge on, our line of sight passes through the torus, hiding the broadline region and revealing only narrow lines. This orientation-based unification model provides a powerful framework for interpreting the variety of active galactic nuclei. The torus is composed of dusty molecular gas that absorbs ultraviolet and optical radiation and re-emits it in the infrared. Its thickness and composition depend on the inflow of material and the heating by the central engine. In some models, the torus is clumpy, consisting of many individual clouds orbiting at different radii. These clouds can obscure the central region intermittently, leading to changes in the observed spectrum. In other models, the torus is continuous and geometrically thick, supported by radiation pressure and turbulence. The exact structure remains a subject of active research, but its existence is strongly supported by observations. Orientation explains why some quasars show broad lines while others do not. When we observe a quasar through the equatorial plane of the torus, the broadline region is hidden. and only the narrow lines and the obscured continuum are visible. Such objects are classified as Type II active galactic nuclei. When we observe through a poleward opening, we see the broad lines and classify the object as Type I. Intermediate viewing angles can produce partial obscuration, leading to hybrid characteristics. This simple geometric model accounts for many observed differences without invoking intrinsic variations in the central engine. Beyond the torus, polarizing material can scatter light into our line of sight. In Type II quasars, although the direct view of the broadline region is blocked, photons can scatter off electrons or dust above the torus and reach us. The scattered light retains the broadline signature and is often polarized. Observing polarized broadlines in an otherwise narrow line spectrum confirms that the central engine is present and luminous but obscured. This observation provides strong support for the unification model and highlights the importance of scattering in shaping the observed spectrum. Orientation also affects the appearance of jets. When a jet points toward us, its emission is amplified by relativistic beaming, making the object appear brighter and more variable. Such objects are known as blazars and show rapid variability and strong polarization. When the jet is oriented away from us, the emission is weaker, and we may classify the object differently. Thus, the orientation of both the torus and the jet, relative to our line of sight, influences our classification of quasars and helps explain the diversity of observed properties. The torus plays a role in regulating the supply of gas to the central engine. Dust grains can survive in the cooler, outer regions of the torus, but sublimate closer in, creating a boundary known as the dust sublimation radius. Gas that migrates through the torus may lose angular momentum through collisions or interactions with magnetic fields, feeding the accretion disk. The torus may also shield the disk from external radiation and maintain a reservoir of material that can sustain the quasar for millions of years. Understanding the dynamics of the torus is thus essential for understanding the life cycle of quasars. Not all quasars fit neatly into the unification scheme. Some low luminosity radio galaxies appear to lack a broadline region and a substantial torus. These objects may represent a different accretion mode or a stage in the evolutionary sequence. Similarly, differences in black hole spin or accretion rate can lead to variations that are not purely due to orientation. While the unification model provides a useful framework, reality is richer and invites further exploration. Recognizing the limitations of any model reminds us that the universe often defies simple categorizations. The unification model connects seamlessly with the technique of reverberation mapping. By observing how emission lines respond to changes in the continuum, we can infer the size of the emitting region and, combined with the line width, estimate the mass of the black hole. The time delay between continuum and line variations is measured by monitoring the quasar over weeks to months. This method requires careful analysis of light curves and cross-correlation functions. The result is a map, not in space, but in time, that reveals the distance between the disk and the broadline clouds. Such echo mapping provides one of the most direct ways to weigh black holes. Reverberation mapping relies on the principle that light takes time to travel. When the continuum emission brightens, it sends a pulse of radiation outward. The broadline clouds intercept this pulse and re-emit it, but their response arrives at Earth delayed by the extra distance the light must travel. By measuring this delay, we determine the radius of the broadline region. The width of the emission lines tells us the velocity of the gas, and by applying the virial theorem, we can infer the mass of the central object. This technique has been applied to dozens of active galaxies, yielding masses ranging from millions to billions of solar masses. Measuring reverberation requires continuous monitoring and careful data analysis. Variations in the light curve can be subtle, and the delay may vary for different emission lines. Because different ions reside at different radii, the response of each line traces a specific region within the broadline region. By comparing delays and line widths, astronomers can probe the structure and stratification of the gas. In some cases, multiple delays have been observed, indicating a complex distribution of clouds. These observations reveal that the broadline region is not a simple shell, but a layered and dynamic environment. Reverberation mapping has provided critical evidence for the presence of supermassive black holes in quasars. Alternative explanations, such as clusters of stars or exotic objects, cannot account for the rapid response times and high velocities observed. The masses derived from reverberation mapping correlate with the luminosity of the host galaxy's bulge, supporting the idea of coevolution. The technique has also been extended to measure the scale of dusty Tauri by observing time delays between optical and infrared variations. In this way, reverberation mapping bridges the gap between small-scale structures and the broader galactic context. Echoes are not limited to emission lines. Dust in the torus absorbs optical and ultraviolet light and re-emits it in the infrared. When the continuum brightens, the dust warms and radiates more strongly. But the infrared response is delayed by the light travel time to the torus. Measuring this delay provides the size of the torus and helps calibrate the sublimation radius. Such observations complement the emission line reverberation and provide a more complete picture of the quasar's structure. Together, these echoes weave a tapestry of time that reveals distances in a system we cannot resolve spatially. Beyond reverberation mapping, variability itself holds clues to the quasar's inner workings. Quasars are not steady beacons. They flicker and flare on timescales from minutes to years. Short-term fluctuations may arise from instabilities in the accretion disk or the corona. Intermediate timescale variations could reflect changes in the supply of gas or magnetic field configurations. Long-term trends may result from evolutionary changes in the accretion rate or interactions with the host galaxy. Studying variability across these timescales reveals the dynamical processes at play and challenges our ability to model complex systems. In the optical band, quasars can vary by a few percent on timescales of days and by tens of percent over months to years. Rapid variability on intra-night timescales is rare, but has been observed in some blazars, where relativistic beaming amplifies fluctuations. Month-to-month variations are common, with amplitudes increasing at shorter wavelengths. These variations often exhibit a bluer when brighter behavior, implying that the spectrum becomes hotter as the luminosity increases. Such trends hint at changes in the temperature distribution of the accretion disk or the addition of a hot component during flares. X-ray variability tends to be more pronounced than optical variability. The high-energy photons originate from the innermost regions and respond quickly to changes in the accretion flow. Flares and dips can occur on timescales of hours, reflecting the small size of the emitting region. In some quasars, quasi-periodic oscillations have been observed, which might correspond to instabilities in the disk or the orbits of hotspots near the last stable orbit. By analyzing the power spectra of light curves, astronomers can identify characteristic timescales and compare them with theoretical predictions. Long-term variability over years to decades can reveal secular changes in the quasar. Gradual brightening or dimming may reflect variations in the mass accretion rate, while sudden transitions can signal a change in accretion mode. Some quasars have been observed to shut down their bright phase and become quiescent, only to reignite later. Others show extreme outbursts that exceed their typical luminosity by large factors. Monitoring these changes provides insight into the life cycle of quasars and the factors that trigger and quench their activity. Variability is not purely random. It often exhibits correlations between different wavelengths. For example, a flare in the ultraviolet may precede a flare in the optical by a few days, indicating that the disturbance propagates outward through the disk. Similarly, changes in the optical may precede changes in the infrared, reflecting the reprocessing of light by dust. Cross-correlating light curves at different wavelengths can reveal the causal relationships between components. Such multi-wavelength studies are essential for building a coherent model of the quasar's inner workings. Statistical studies of quasar variability across large samples reveal trends with luminosity, wavelength, and black hole mass. More luminous quasars tend to vary less on short timescales, possibly because their larger disks average out fluctuations. Lower mass black holes exhibit faster variability, consistent with their smaller size. The variability amplitude increases towards shorter wavelengths, indicating that the inner, hotter regions fluctuate more than the outer, cooler regions. These trends provide empirical constraints for models of accretion disk turbulence and instabilities. While variability offers a window into the physical processes at work, it also poses challenges for observations and modeling. To capture rapid fluctuations, high-cadence monitoring is required, while long-term trends demand sustained observations over years. Instruments across the electromagnetic spectrum must coordinate to produce simultaneous light curves, enabling cross-wavelength analyses. The wealth of data generated by time-domain surveys promises to shed new light on quasars, but it also calls for sophisticated statistical tools to extract meaningful patterns. Embracing the time dimension transforms quasars from static objects into dynamic laboratories for high-energy astrophysics. Having traversed the temporal dimension, we now turn to the spectral dimension. A quasar's spectrum is not a single color, but a combination of emission across the entire electromagnetic spectrum, from radio waves to gamma rays. Each band of radiation carries unique information about different physical processes and regions within the quasar. The radio emission often originates from the jets, while the infrared comes from dust. The optical and ultraviolet light trace the accretion disk, and the X-rays reveal the corona. At the highest energies, gamma rays may be produced in jets through inverse Compton scattering or pion decay. By assembling these pieces, we build a comprehensive picture of the quasar's energy output. In the radio band, synchrotron emission from relativistic electrons spiraling in magnetic fields dominates. Radio-loud quasars produce powerful jets that emit strongly at these wavelengths, forming lobes and hotspots far from the central engine. Radio-quiet quasars emit much less radio power, and their radio emission may be confined to the innermost regions. The radio spectrum often follows a power law shape, with variations corresponding to changes in the magnetic field strength and electron energy distribution. Observing the radio emission provides insight into jet dynamics and the impact of relativistic beaming. Moving into the infrared, we encounter the thermal emission from dust. The torus absorbs ultraviolet and optical radiation from the accretion disk and re-emits it at longer wavelengths. This produces a broad bump in the spectral energy distribution, peaking at wavelengths of tens of micrometers. The shape and peak of this bump depend on the temperature and distribution of the dust. Infrared observations can reveal the size of the torus and the presence of star formation in the host galaxy. In radio-loud quasars, the infrared may also include contributions from synchrotron emission that extends from the radio into higher frequencies. The optical and ultraviolet bands are dominated by the accretion disk's thermal emission. This big blue bump peaks in the far ultraviolet and is characterized by a steep rise in the spectral energy distribution. The precise shape of the bump encodes the temperature profile of the disk and can be modeled using thin disk theory. Superimposed on this continuum are broad and narrow emission lines from the gas that surrounds the disk. Variations in the continuum and lines across the optical and ultraviolet provide clues to the structure of the disk and the broad line region. In the X-ray band, the corona takes center stage. The spectrum here is often described by a power law component with a high energy cutoff, reflecting the temperature and optical depth of the corona. On top of this continuum, reflection features appear, including the iron K alpha line and the Compton hump. The relative strengths of these features depend on the geometry and ionization state of the disk and corona. Studying the X-ray spectrum allows astronomers to probe the innermost regions of the accretion flow and test models of Comptonization and reflection. At gamma-ray energies, only the most extreme quasars emit significant radiation. Blazars, in particular, produce gamma rays through inverse Compton scattering of low-energy photons by highly energetic electrons in the jets. In some cases, interactions between accelerated protons and ambient photons can produce pions that decay into gamma rays. The detection of gamma-ray emission requires sensitive space-based instruments and provides insights into particle acceleration and jet physics. Observations across the electromagnetic spectrum reveal that quasars are multi-component systems with energy output spanning many orders of magnitude. The spectral energy distribution of a quasar is not static. It evolves as the accretion rate changes, as the dust heats and cools, and as the jets flare and fade. Long-term monitoring across multiple bands reveals that the relative contributions of the disk, corona, torus, and jets can vary. In some periods, the disk may dominate the output, while at other times, the jet or the torus may become more prominent. Such changes reflect shifts in the physical conditions and the interplay of different processes. The living spectrum of a quasar tells a story of continuous transformation and adaptation. By combining observations at all wavelengths, astronomers can construct a comprehensive picture of the energy budget. The area under the spectral energy distribution curve represents the total power output of the quasar. Comparing this power with the inferred mass accretion rate provides a measure of the radiative efficiency. In turn, the efficiency constrains the spin of the black hole and the nature of the accretion flow. Observations reveal that quasars can radiate with efficiencies of several percent up to tens of percent, indicating that accretion onto rotating black holes is highly efficient at converting mass into energy. Our journey through the engines of brilliance has taken us from the dark heart of supermassive black holes, through the luminous disks that convert gravitational energy into radiation, to the hot coronae that upscatter photons into X-rays. We have traced the tangled magnetic fields that thread the disk and launch jets, considered how those jets extract spin energy and propagate across the universe, and examined the spectral lines that reveal the kinematics of the gas. We have explored the role of dust and orientation in shaping what we see, used echoes to map unseen regions, and celebrated the flickering variability that makes quasars dynamic. Finally, we have charted the full spectrum from radio to gamma rays, appreciating the diversity of processes that contribute to the quasar's light. As we reflect on these engines and prepare to explore their broader context, we leave the jets still streaming and the spectra still evolving. In the next part, our gaze will extend into the universe, examining how quasars illuminate cosmic history and influence the growth of galaxies. The story of quasars is far from over, and their light continues to guide our understanding of the cosmos. For now, let us rest with the images of swirling disks, rising jets, and shimmering lines, and allow the echoes of these engines to resonate within us. The night is deep, the universe vast, and the quest for understanding ever open. Supermassive black holes may begin their lives as the remnants of the first massive stars, or as direct collapses of primordial gas clouds. In the early universe, dense regions collapsed under gravity, forming seed black holes that could have been hundreds or thousands of solar masses. These seeds grew through accretion and mergers, gradually building up to millions or billions of solar masses. The process of growth is thought to be limited by the Eddington rate, but episodic bursts of super-Eddington accretion could accelerate the buildup. Observing quasars at high redshift provides clues to how rapidly these giants formed. Galaxy mergers play a crucial role in fueling the growth of supermassive black holes. When two galaxies collide, tidal forces funnel gas toward the center, triggering bursts of star formation and feeding the black hole. As the black holes from each galaxy spiral together, they may eventually merge, emitting gravitational waves and forming a more massive hole. The merging process can also spin up the black hole, increasing its ability to launch jets. Thus, the history of a quasar is intertwined with the cosmic dance of galaxies across billions of years. Feedback from the quasar can regulate the growth of the black hole and the host galaxy. Powerful winds and jets can blow gas out of the galactic nucleus, quenching star formation and limiting the supply of fuel. In other cases, feedback may compress gas clouds and trigger new star formation, enriching the environment with heavy elements. The balance between accretion and feedback shapes the evolution of galaxies and helps explain the observed correlation between black hole mass and bulge properties. Understanding this balance remains a major goal of astrophysics. The accretion disk itself is a laboratory for exotic physics. Within its turbulent layers, magnetic fields twist and reconnect, viscosity emerges from chaotic motions, and radiation interacts with matter in extreme regimes. The vertical structure of the disk is shaped by hydrostatic equilibrium, balancing the pull of gravity and the pressure of gas and radiation. Temperature gradients cause the disk to emit at different wavelengths, and chemical reactions within the disk can lead to the formation of molecules and dust. Exploring the microphysics of disks links the macroscopic behavior we observe to the fundamental laws of nature. Disks can host winds that carry away angular momentum and mass. These winds are launched when radiation pressure, magnetic forces, or thermal pressure overcome gravity. In some models, line-driven winds arise from the pressure of ultraviolet photons on metal ions, while in others, magnetocentrifugal processes fling material outward along field lines. Disk winds can produce absorption features in quasar spectra, revealing their presence. They may also help to collimate jets and contribute to feedback on galactic scales. The interplay between winds and accretion adds another layer of complexity to quasar physics. Instabilities within the disk can lead to dramatic changes in accretion rate. Thermal instabilities occur when heating and cooling processes respond differently to temperature, causing runaway, brightening, or dimming. Viscous instabilities arise from feedback between surface density and angular momentum transport, potentially leading to ring-like structures. Gravitational instabilities can occur in the outer parts of the disk, triggering fragmentation and star formation. These processes can imprint themselves on the variability of the quasar and may be responsible for some of the quasi-periodic oscillations observed. Understanding them requires detailed numerical simulations and sophisticated theoretical models. The corona is not a single monolithic entity. It may comprise multiple zones with different temperatures and densities. A warm, optically thick corona may lie just above the disk, producing soft X-ray excesses, while a hotter, optically thin corona produces the harder X-ray power law. The boundary between these zones may be blurred, with continuous gradients in temperature and density. Interactions between zones can lead to complex spectral features and variability patterns. Investigating the layering of the corona helps to explain the diverse X-ray spectra observed among quasars. In high-energy environments, pair production can occur. When photons of sufficient energy collide, they can create electron-positron pairs, adding to the plasma of the corona. These pairs can, in turn, annihilate, producing gamma rays. The balance between pair production and annihilation influences the temperature and opacity of the corona. In some cases, runaway pair production can lead to a pair plasma that alters the Comptonization process. Including these quantum electrodynamic effects enriches our understanding of the extreme conditions around black holes. The shape of the X-ray spectrum can reveal whether the corona is compact or extended. A compact corona near the black hole produces a steeper reflection spectrum due to gravitational redshift and light bending, while an extended corona yields different reflection signatures. Time lags between X-ray and optical variations can also distinguish between different geometries. Future missions with high spectral resolution and timing capabilities will provide sharper views of these regions. In this way, the corona becomes not just a source of high-energy photons, but a probe of spacetime near the horizon. Magnetically arrested disks represent a regime in which the magnetic field grows so strong that it can disrupt the accretion flow. In this state, the inflowing gas drags in large-scale magnetic flux, which accumulates near the black hole. When the magnetic pressure becomes comparable to the ram pressure of the inflow, accretion slows, and the field lines can become dynamically dominant. Such disks are efficient at launching powerful jets, as the strong fields provide a conduit for extracting spin energy. The onset of a magnetically arrested state may correspond to episodes of intense jet activity and high variability. Morphological differences in radio jets are often classified into two types, known as Fanaroff-Riley classes. Type 1 jets decelerate quickly, becoming diffuse and plume-like, while Type 2 jets remain collimated and terminate in bright hotspots. The dichotomy may be related to the environment and the power of the jet, with more powerful jets able to punch through the intergalactic medium without disruption. The magnetic field strength and configuration at the base of the jet likely influence which class arises. Studying these differences helps to connect the microphysics of launching to the macroscopic appearance of radio sources. Relativistic magneto-hydrodynamic simulations have shed light on how jets propagate through their environment. These simulations show that helical magnetic fields can stabilize jets against certain instabilities, while Kelvin-Helmholtz instabilities at the interface with the ambient medium can still cause mixing. Shocks develop naturally in the flow, accelerating particles and producing radiation. Comparison between simulated emission maps and observations allows researchers to test models and refine parameters. As computational power grows, simulations will continue to reveal the interplay between magnetic fields, plasma, and relativity in shaping jets. Gravitational redshift can influence the profiles of broad emission lines. Light emitted close to the black hole loses energy as it climbs out of the gravitational well, shifting the line to longer wavelengths. The effect is strongest for gas closest to the horizon and can lead to asymmetric line profiles. By modeling these profiles, astronomers can infer the location of the emitting gas and the depth of the potential well. This gravitational imprint on the spectra provides another test of general relativity in strong field regimes. Microlensing by stars in a foreground galaxy can magnify different regions of a distant quasar. Because the broad line region is more compact than the narrow line region, microlensing can differentially magnify the broad lines relative to the continuum and narrow lines. Observing these microlensing events reveals the size and structure of the emitting regions with remarkable precision. Such natural experiments complement reverberation mapping and provide an independent measure of the quasar's inner geometry. They also underscore the interconnectedness of cosmic structures across vast distances. An intermediate line region may exist between the broad and narrow line regions. This zone would contain gas with velocities and densities intermediate between the extremes, producing lines of moderate width. Some spectra show evidence for such components, often in the form of shoulders on broad lines or separate peaks. The physical origin of this region could be a transition zone where the disk wind interacts with the torus, or where the outflow cools and slows. Identifying and modeling the intermediate line region enrich our understanding of the full kinematic and ionization structure of quasar environments. Clumpy torus models propose that the obscuring material is composed of discrete clouds rather than a continuous distribution. These clouds orbit the black hole and have a range of sizes and optical depths. As clouds move in and out of our line of sight, they can cause variability in the obscuration, leading to changes in the observed spectrum. The clumpy model explains why some quasars show partial covering and why infrared emission does not always correlate simply with orientation. High-resolution infrared interferometry is beginning to resolve these structures, offering glimpses of the torus's granular nature. The composition of the dust grains in the torus affects the spectrum. Silicate grains produce broad emission features at wavelengths around 10 and 18 micrometers, while graphite grains contribute to absorption in the ultraviolet. The relative abundance of different grain types provides clues about the chemical enrichment history of the host galaxy. Observing silicate emission or absorption features can indicate whether we are viewing the hot inner wall of the torus or the cooler outer regions. These spectral signatures help disentangle the geometry and composition of the obscuring material. Star formation often coexists with the quasar in the central region of the host galaxy. Young stars heat dust and contribute to the infrared emission, complicating the interpretation of the torus. In some cases, a circumnuclear starburst may dominate the far infrared output, masking the quasar's contribution. By combining spectroscopic diagnostics of star formation with mid-infrared spectral features, astronomers can separate these components. The interplay between quasar activity and star formation influences the growth of the galaxy and leaves imprints on the dust emission. Understanding this interplay is key to placing quasars in their galactic context. Cross-correlation analysis is central to reverberation mapping. Light curves of the continuum and emission lines are compared to determine the lag that maximizes the correlation. This lag corresponds to the light travel time from the source of the continuum to the line-emitting gas. Statistical techniques account for irregular sampling and noise, ensuring that the measured lag is robust. The uncertainties in the lag propagate into uncertainties in the black hole mass, highlighting the importance of high-quality, long-duration monitoring campaigns. Velocity-resolved reverberation mapping goes beyond measuring a single lag by examining how different parts of the line profile respond over time. This technique allows astronomers to map the kinematic structure of the broadline region. For example, the blue and red wings of a line may respond at different times, indicating inflow or outflow. By reconstructing the velocity delay map, researchers can infer whether the gas is in a virialized disk, a wind, or another configuration. These maps provide a three-dimensional view of the region that cannot be obtained by any other means. Reverberation mapping has the potential to contribute to cosmology. By calibrating the relationship between the size of the broadline region and the quasar's luminosity, quasars can be used as standard candles. Measuring distances to quasars across a range of redshifts could provide an independent probe of the expansion history of the universe. This application remains challenging due to scatter in the size-luminosity relationship and the need for extensive monitoring. Nevertheless, it illustrates how studying the inner workings of quasars can have implications for our understanding of the cosmos at large. The timescales of variability correspond to physical processes within the accretion disk. The orbital timescale defines how long it takes matter to complete a circular orbit at a given radius, ranging from hours near the black hole to years farther out. The thermal timescale describes how quickly the disk can adjust its temperature, typically longer than the orbital time. The viscous timescale, associated with angular momentum transport and mass inflow, is even longer, often spanning thousands of years. Variability observed on human timescales likely reflects a combination of orbital and thermal processes, modulated by fluctuations in the supply of gas. Magnetic reconnection events in the corona can produce rapid flares. When twisted magnetic field lines break and reconnect, they release energy suddenly, heating the plasma and accelerating particles. These events may produce X-ray or gamma-ray flares that rise and fall over hours. On longer timescales, changes in the magnetic field configuration can alter the efficiency of angular momentum transport, leading to variations in the accretion rate. Such changes may manifest as weeks-long fluctuations in the optical and ultraviolet bands. The connection between magnetic activity and variability underscores the importance of magnetism in quasar dynamics. External factors can also induce variability. Gravitational microlensing by stars in a foreground galaxy can amplify the quasar's light on timescales of months to years, creating peaks in the light curve that are not intrinsic. Dust obscuration events, where a cloud passes in front of the quasar, can cause dips in brightness that recover once the cloud moves on. Interactions with companion galaxies may trigger bursts of accretion by disturbing gas in the host. Distinguishing between intrinsic and extrinsic variability requires careful analysis and often multiple lines of evidence. Each case adds to the tapestry of quasar behavior. Differences between radio-loud and radio-quiet quasars manifest across the spectrum. Radio-loud quasars tend to have a stronger synchrotron component that can extend into the infrared and optical, producing a flatter spectral slope. They also often exhibit stronger X-ray emission relative to the optical, possibly due to a more active corona or contribution from the jet. Radio-quiet quasars, by contrast, have spectra dominated by thermal emission from the disk and dust, with weaker radio and X-ray components. These differences hint at underlying variations in black hole spin, magnetic field strength, and accretion mode. The near-infrared inflection point, where the spectrum transitions from the disk-dominated big blue bump to the dust-dominated infrared bump, marks a change in the emission mechanism. At around 1 micron, the contribution from the host galaxy's stellar population may also become significant, especially in lower luminosity quasars. Careful decomposition of the spectrum into disk, dust, and stellar components is necessary to isolate the quasar's intrinsic emission. This decomposition allows for more accurate measurement of the quasar's luminosity and, by extension, the mass accretion rate and radiative efficiency. Multi-wavelength surveys have revealed that the spectral energy distribution of quasars evolves with redshift. High redshift quasars often show stronger ultraviolet emission relative to the infrared, possibly reflecting lower dust content or differences in accretion physics. The radio loud fraction also evolves, with early quasars more likely to exhibit strong jets. Observations with next-generation telescopes in the submillimeter and infrared bands are shedding light on the dust properties of early quasars. These trends provide insight into the growth of black holes and the assembly of galaxies in the young universe. Beyond their immediate surroundings, quasars influence the universe on large scales. Their radiation contributes to the ionization of intergalactic gas, particularly during the epoch of reionization. High-energy photons from early quasars may have helped to reionize helium in the intergalactic medium, altering its thermal history. The distribution and luminosity of quasars across cosmic time inform models of how the universe transitioned from neutral to ionized. Understanding this role requires connecting the microphysics of the quasar engine to the macroevolution of cosmic structures. Quasar feedback shapes the formation and evolution of galaxies. Powerful outflows can regulate star formation by removing or heating gas in the host halo. At the same time, the injection of energy and momentum can promote turbulence and mixing, redistributing metals and altering the chemical evolution. Observations of large-scale outflows and simulations of galaxy formation highlight the importance of quasar-driven feedback. Incorporating realistic quasar models into cosmological simulations remains a frontier challenge, linking the detailed physics we have explored to the grander narrative of galaxy evolution. In the realm of multi-messenger astronomy, quasars may contribute to gravitational wave signals. Mergers of supermassive black holes in quasar-host galaxies emit gravitational waves at frequencies accessible to future space-based detectors. Detecting these signals will provide direct measurements of black hole masses and spins and offer new tests of general relativity. Coupling gravitational wave observations with electromagnetic observations of quasars will open a new window into the growth and dynamics of black holes. The anticipation of such discoveries underscores the evolving nature of quasar research. The coming decade promises transformative advancements in our understanding of quasars. New telescopes and instruments will extend our reach in time and wavelength, enabling us to observe quasars in greater detail and at earlier epochs. Surveys like the Vera Rubin Observatory will capture variability across vast samples, while missions like the James Webb Space Telescope and Athena will probe the infrared and X-ray regimes with unprecedented sensitivity. These facilities will provide the data needed to refine models of accretion, feedback, and cosmic evolution, building upon the foundations laid by previous generations. Light from distant quasars sometimes passes near intervening galaxies on its way to us. The gravity of these foreground masses bends the path of the photons, creating multiple images, arcs, or rings in the sky. The delays between these images carry information about the geometry of the universe and the mass of the lensing galaxy. By monitoring the flickering of a quasar in the different images, astronomers can measure the light travel time differences and infer the expansion rate. In this way, quasars become not only beacons, but also cosmological tools. As the quasar's light streams across billions of light years, it encounters clouds of hydrogen gas in the intergalactic medium. Each cloud imprints a narrow absorption line on the quasar's spectrum at a wavelength corresponding to the redshift of the cloud. The resulting forest of lines, known as the Lyman alpha forest, maps the distribution of matter along the line of sight. By analyzing the pattern and strength of these lines, cosmologists reconstruct the structure of the cosmic web and the evolution of the intergalactic medium. Quasars thus illuminate not only their own environs, but also the vast spaces between galaxies. The jets emanating from quasars accelerate particles to relativistic speeds, producing not only electromagnetic radiation, but also high-energy cosmic rays. When these particles interact with ambient matter, or radiation fields, they can generate neutrinos and gamma rays. Detections of high-energy neutrinos coincident with blazar flares hint at quasars as sources of cosmic neutrinos. The link between the electromagnetic and neutrino outputs offers a multi-messenger view of quasar jets. Understanding these connections will help unravel the processes that drive particle acceleration and energy dissipation in extreme environments. Beyond the bright core, the energy carried by jets inflates enormous lobes and bubbles in the circumgalactic medium. These structures, visible in radio wavelengths, can span hundreds of thousands of light years and deposit kinetic energy far from the nucleus. Shock waves generated by the jets heat the gas, suppressing or triggering star formation depending on the conditions. The morphology of these lobes reflects both the power of the jet and the density of the surrounding medium. Observing these large-scale features provides a bridge between the microphysics of the engine and the macroscopic impact on the galaxy. The fueling of quasars depends critically on the supply of gas delivered to the galactic center. Interactions and mergers between galaxies can funnel gas inward through tidal torques, providing the raw material needed to ignite accretion. Even minor interactions, such as the passage of a satellite galaxy, can perturb orbits and trigger inflows. Once the fuel supply diminishes, the quasar fades, perhaps to be reawakened by a future encounter. These episodic fueling events contribute to the observed diversity of quasar luminosities and lifetimes, tying the activity of the nucleus to the dynamical history of its host. The spin of the black hole may not always align with the rotation axis of the host galaxy or the incoming gas. Misalignments can arise from chaotic accretion events or mergers with other black holes. When the spin and the disk are misaligned, the inner regions of the disk can warp and precess under the influence of relativistic torques. Such warping may influence the direction and stability of jets and modulate the observed emission. Over time, accretion can realign the spin with the inflowing gas, illustrating a feedback loop between the engine and its environment. In thinking about quasars, we must remember the vast stretches of time their light has traversed. Photons we collect today left their sources when the universe was young, passing through epochs of change we can only imagine. Along the way, cosmic expansion stretched their wavelengths and diluted their energy, yet they arrive bearing coherent information about their origin. Watching a quasar flicker is to watch an event from a time before our planet existed, an act that bridges human experience with cosmological time. Such contemplation anchors our place in the universe and deepens the sense of mystery. In the forthcoming chapters, we will delve into how quasars are used to probe the cosmos at large. We will follow their light as it traces the distribution of matter, as it is bent and delayed by gravity, and as it interacts with the intergalactic medium. We will consider the role of quasars in cosmic reionization and their use as lighthouses to calibrate distances. Each of these topics builds upon the engine physics we have explored, extending the story from the heart of the quasar to the cosmic horizon. The adventure continues, inviting us to keep exploring. Some quasars show evidence for powerful winds emerging from the accretion disk in the form of broad absorption lines. These troughs, shifted to the blue side of ultraviolet resonance lines, indicate gas moving outward at tens of thousands of kilometers per second. The acceleration may be driven by radiation pressure or magnetocentrifugal forces, depending on the conditions in the disk. These winds can carry away angular momentum, regulating the accretion rate, and may seed the intergalactic medium with metals. The visibility of broad absorption lines depends on our viewing angle, offering another clue about the three-dimensional structure of the quasar. New observational techniques promise to deepen our understanding of quasars and their cosmic role. 21-centimeter radio surveys will map neutral hydrogen during the epoch of ionization, revealing how the first quasars carved bubbles in the cosmic fog. Time domain surveys will sample the quasar light curve over decades, uncovering patterns and rare events that challenge current models. Gravitational wave observatories will add another channel, capturing the mergers that build supermassive black holes. Each advance brings us closer to a holistic picture in which quasars are not isolated curiosities, but integral actors in the cosmic narrative. As we prepare to continue our exploration, it is worth pausing to appreciate the interconnectedness of the phenomena we have encountered. The gravitational pull of a black hole shapes the motion of gas. The disk's turbulence feeds the corona and jets. Magnetic fields weave together the fate of matter and energy, and the orientation of dust determines our view. Through variability and spectra, we glimpse the choreography of these components. And through echoes, we measure distances that cannot be resolved. Each thread contributes to a tapestry that stretches from the atomic scale to the cosmic web, inviting us to follow it further in the chapters ahead. With these threads in mind, the next part of our journey will move beyond the engines themselves to examine the influence of quasars on the cosmos. We will explore how the light from these distant beacons illuminates the intergalactic medium, how their feedback shapes the formation of galaxies, and how they serve as probes of fundamental physics. The engines will continue to hum in the background, providing context and energy for the broader story. Our path leads from the intimate to the expansive, weaving together the microcosm of black hole physics and the macrocosm of cosmic evolution. In the meantime, you can let your mind wander through the landscapes we have described, imagining the spiraling disks, the crackling coronae, the twisting magnetic fields, and the far-reaching jets. Picture the clouds in the broad line region responding to a pulse of light, and the dust in the torus glowing in the infrared. Consider the timescales over which these events unfold, some faster than a heartbeat, others longer than a human lifetime. The universe presents us with a symphony of processes, each adding to the harmony of the whole. Listening to this cosmic music prepares us to appreciate the next movements. As night falls and you look up at the stars, remember that behind some of those faint points of light lie quasars, lighthouses from the distant past. Their photons have traveled billions of years to reach us, carrying the signatures of the processes we have explored. Each photon is a messenger from a time when the universe was younger and different, yet governed by the same physical laws. By studying these messages, we not only learn about quasars, but also about the history of the universe itself. Our curiosity links us to these distant engines, forging a connection across space and time. Light travels as a silent messenger across the expanding cosmos, carrying with it the story of its origin. When we observe a distant quasar, we are not just seeing a point of light. We are peering through a tunnel of time. The space between us and the quasar has been stretching for eons, pulling the quasar's light to longer, redder wavelengths. This phenomenon, known as cosmological redshift, turns the quasar's energetic ultraviolet glow into gentle infrared by the time it reaches our telescopes. And in that subtle change of color lies a cosmic clock. The greater the redshift we measure, the longer that light has been in transit, and the farther back in history its journey began. In this way, redshift becomes a kind of time machine, a means to read distance in terms of years gone by. Imagine photons leaving a primordial quasar when the universe was only a few 100 million years old, streaming outward while galaxies and stars form and fade around them. After traveling for billions of years across the expanding fabric of space, those ancient photons finally arrive here and now. By capturing them, astronomers witness a scene from the deep past, preserved in that faint glow. For instance, light from a quasar observed today might have embarked on its voyage nearly 13 billion years ago, when the cosmos was less than 10% of its current age. We see such a quasar not as it is now, but as it was in that distant epoch, a brilliant beacon shining over an almost unimaginably young universe. It is humbling to recognize that when we gaze at these remote beacons, we are looking at a younger cosmos directly. A photon that began its journey long before Earth even formed is only now reaching our eyes. In this way, a telescope becomes not just a tool of observation, but a means of time travel. We peer across unimaginable gulfs of space and years, witnessing chapters of cosmic history unfolding in the sky. The night sky, filled with ancient light, connects us to epochs otherwise beyond reach. Each distant quasar, a portal to the universe's youth. Every high redshift quasar is thus a messenger from a bygone era. Each one's redshift value, denoted by Z, tells us how dramatically the universe has expanded since light left the source. A modest redshift might correspond to a time when multicellular life was emerging on Earth, whereas an extreme redshift signifies an era long before our planet existed. The most far-flung quasars known have astonishing redshifts. For example, one quasar has a redshift of approximately 10.1, meaning its light has travelled an estimated 13.7 billion light-years to reach us. To look at this single pinpoint in the sky is to gaze back to a time only around 450 million years after the Big Bang. Through these remote beacons, we can survey the cosmic dawn, when the first generations of stars and galaxies were just beginning to chase away the darkness of the early universe. This ability to see the past directly is one of astronomy's quiet miracles. The night sky is filled with stars and nebulae relatively nearby, but beyond them lie faint quasars whose light left when the cosmos was in its infancy. By measuring their redshift, we decode how far their light had to travel, and thus how old the universe was when that light set out. With each increment in distance, we peel back another layer of cosmic history. A quasar with a high redshift appears to us as it was billions of years ago. In effect, high redshift quasars are windows onto the universe's youth. Observing them, astronomers become time travelers, piecing together how things looked and what processes were at play in eras otherwise beyond reach. The concept of redshift as a cosmic time machine lends a subtle, almost poetic pace to our exploration of quasars. We realize that the farther we look, the earlier the chapter of the universal story we are reading. When we detect the spectral signature of hydrogen from a quasar at extreme redshift, we know those photons left when atoms in the universe were first coming together in protogalaxies. When we see the light of a quasar dimmed by intervening gas, we are glimpsing the state of intergalactic matter eons in the past. In essence, distance in astronomy equates to time, and redshift is the key that unlocks that relationship. Through it, quasars serve not only as lighthouses in space, but also as beacons in time, guiding our understanding of cosmic evolution across epochs. Floating in the darkness, each quasar's glow is a reminder of how young the universe once was, The photons we catch today might have begun their journey when the universe was only a tiny fraction of its current age. Back then, the galaxies we know were still in infancy or not yet formed. The cosmos was a sea of hydrogen clouds and nascent stars. And yet, in that youthful universe, quasars, powered by newborn giant black holes, were already shining brilliantly. Their light, stretched and weary from the long passage, arrives as a gentle whisper from that era. By listening to that whisper, we learn how the early cosmos grew and transformed. As we tune into these distant signals, we set the stage to meet the quasars themselves, especially those extraordinary ones that appeared so soon after the Big Bang. These high redshift quasars are more than just distant points. They are puzzles in their own right. They lead us to wonder how something so bright and powerful could form in such a young universe. With redshift guiding our way through time, we prepare to encounter the first giants among quasars, the colossal black holes that somehow blazed to life in the universe's first billion years. They emerge from the darkness of the young cosmos as almost implausibly bright stars on the cosmic stage. In the first billion years of cosmic history, these first giants, quasars hosting black holes of immense mass, were already shining across space. The discovery of a quasar, just 770 million years after the Big Bang, powered by a black hole 2 billion times the mass of our Sun, sent ripples of astonishment through the astronomy community. Such a hefty black hole appearing so early is difficult to fathom. One researcher likened it to rolling a small snowball down a hill and finding it suddenly grown to the size of a house. Indeed, it gives astronomers a headache to imagine how a black hole could bulk up to billions of solar masses in so short a time. This is the riddle of rapid growth, a puzzle written in the light of the earliest quasars. By the epoch of 1 billion years after the Big Bang, multiple quasars with supermassive black holes were already in full blaze. These youthful quasars tell us that the ingredients for building giant black holes assembled swiftly in the infant universe. Even at redshifts around 6 to 7, when the universe was only 5 to 7% of its current age, we observe quasars whose central masses reach 1 billion suns or more. Each such object is a marvel of early formation. Consider that a black hole feeding on gas has a built-in speed limit. It can only swallow material so fast before the energy released blows away the rest of the infalling gas. Yet these early quasars somehow packed on weight at breakneck pace. If one started as a small remnant of the very first stars, perhaps only a few dozen solar masses, normal growth rates would simply not get it to 1 billion solar masses by this time. The timeline is too tight under ordinary conditions. There just isn't enough cosmic time for a light seed to grow into a leviathan, not without special circumstances or new physics. This realization has profound implications. It suggests that the birth and feeding of the earliest black holes must have been extraordinary. Either the seeds they grew from were much bigger than any modern stellar remnant, or these black holes found a way to eat far more efficiently, and perhaps faster, than we thought possible. Astronomers have posited that some black hole seeds could form directly from the collapse of massive primordial gas clouds, skipping the intermediate step of a star, thereby starting off tens of thousands of times heavier than a typical stellar mass black hole. Others propose that early black holes might occasionally devour matter at rates above the usual theoretical limit, in short bouts, to speed up their growth. One way or another, the mere existence of the first giant quasars demands something happened to turbocharge black hole formation in the young universe. We now know of dozens of these cosmically ancient quasars. With each new discovery, the record for the earliest or most massive early black hole has inched further back in time. One particularly far-flung beacon, detected in faint infrared and X-ray light, dates to about 450 million years after the Big Bang. Its redshift of around 10 suggests a truly primordial origin, and yet it harbours a supermassive black hole already in place. Every such find reinforces how quickly the universe went from a pristine state, containing no stars or galaxies at all, to one hosting not just galaxies, but galaxies with central black holes as massive as small galaxies themselves. The first billion years after cosmic dawn clearly was a time of astonishingly rapid growth for these gravitational giants. In recent years, more record-breaking quasars have been uncovered. In 2018, astronomers discovered a quasar at redshift 7.5, only about 700 million years after the Big Bang, hosting a black hole nearly a billion solar masses. Another, announced in 2021 at redshift 7.6, contains an estimated 1.6 billion solar mass black hole, and shines when the universe was a mere 5% of its current age. Each new find reinforces the same conundrum. It appears the universe wasted little time in assembling these cosmic giants, challenging theorists to explain their rapid appearance. The prevalence of bright quasars in those early epochs also hints that the conditions then were ripe for black holes to feast. Gas was abundant and dense in young proto-galaxies, providing rich fuel. The very fact that quasars were much more common in the distant past than they are today shows that we are seeing an era when supermassive black holes were much more common than they are today. Holes were actively accumulating mass at an exceptional rate. It was a time of cosmic exuberance, when massive black holes blazed as quasars, wherever fuel and a deep potential well were found together. Looking at the sky today, we catch only the faint afterglow of that period. A handful of relic quasars at extreme distances, their light stretched by cosmic expansion. Yet those few we detect speak volumes about their unseen brethren. They imply that in the youthful universe, quasars might have been sprouting in many newborn galaxies, each one a dramatic bonfire fueled by infalling gas. Confronted with these early, overgrown black holes, astronomers are driven to refine their theories of cosmic evolution. How did the universe manage to produce objects so massive, so fast? This question guides us directly into an exploration of black hole seeds, the initial kernels from which supermassive black holes grew. To solve the mystery of the first giants, we must trace them back to their roots. What seeds could they have originated from? And what special pathways allowed those seeds to swell into billion solar mass quasars in such a brief span of time? In the next part of our journey, we delve into the realm of nascent black holes, the seeds of darkness that gave rise to the cosmic leviathans shining in the early ages of the universe. Deep in the primordial night, before galaxies were fully formed, the first black hole seeds were sown. These seeds of darkness came in different forms. The most straightforward possibility is that they were the corpses of the very first stars. In the young universe, massive stars lived fast and died in spectacular fashion, sometimes leaving behind black holes, weighing perhaps a few dozen or a few hundred times the sun. Such stellar remnants are often called light seeds. If many of them lurked in the dense cores of early protogalaxies, they could serve as the starting points for growth. However, as we have seen, there is a catch. A black hole that begins its life, this small, has a daunting task to reach a billion solar masses in only a few 100 million years. Even under ideal conditions, steadily gorging on gas at the maximum rate allowed, a light seed would struggle to bulk up that dramatically in such a short span. It's like trying to grow a tree from a sapling to a giant redwood overnight. This timing problem led scientists to suspect that something more was at play. Another, more exotic pathway posits the existence of heavy seeds, black holes born already much larger than any normal star could produce. Instead of forming from a star, these could form directly from the collapse of a massive cloud of gas in the early universe. Imagine a young galaxy in the making, a great cloud of hydrogen tens of thousands of times the mass of a star, collapsing inward without fragmenting into smaller pieces. If conditions were just right, for example, if the gas was almost pure hydrogen and helium, and if radiation from nearby newborn galaxies kept it from cooling and breaking into stars, this cloud might implode directly into a black hole containing the mass of 100,000 suns or more. No supernova explosion, no intermediate stars, just a direct plunge from diffuse gas to dense singularity. Such a titanic birth would create a ready-made black hole seed, far heavier at birth than the light seeds from star deaths. And with that head start in mass, this heavy seed would have a much easier road to becoming a supermassive black hole. Astrophysicists have theorized various scenarios in which heavy seeds could form. One leading idea involves a sort of cosmic nurture, a proto-galaxy that grows up under special circumstances. Picture two infant galaxies near each other in the early universe. One begins forming stars, while the other's growth is stunted by the flood of radiation from its neighbor. In that second galaxy, starlight from next door keeps the gas hot and prevents the usual birth of myriad small stars. Deprived of the chance to fragment into stars, its gas might remain a single vast cloud. Eventually, that cloud's self-gravity would overwhelm any remaining pressure, and it would collapse in one fell swoop. The result: a massive black hole forming at the galaxy's center, perhaps with an initial mass in the tens or hundreds of thousands of solar masses. In essence, the galaxy skips the normal process of stellar evolution and goes straight to having a black hole. Such a black hole could then quickly accrete more gas or merge into the larger companion galaxy, planting a seed of substantial size in the heart of what will become a new quasar. These ideas of heavy seeds were once largely speculative, but they have gained traction as we confront the hard evidence of early quasars. The discovery of extremely distant quasars, like UHZ1, with properties hinting at an outsized black hole in place just 450 million years after the Big Bang, provides strong support for the heavy seed hypothesis. It's increasingly clear that the universe's first black holes did not all start from the same template. Nature likely employed multiple routes to grow these cosmic Goliaths. Some black holes may have begun as ordinary light seeds and managed, through exceptional luck or conditions, to rapidly binge on gas and merge with one another. Others, perhaps like the ones powering the very earliest quasars, might have been born big, the outcome of rare direct collapse events in primordial environments. Astronomers now speak of these possibilities not just in theory, but with observational clues in hand, an alignment of evidence that the early universe was seeding black holes in diverse ways. Having a viable seed, whether light or heavy, was only the beginning. The seed then had to grow. In a young galaxy rich with unclaimed gas, a black hole seed would begin accreting matter, pulling in nearby gas and even stars, heating them to brilliant temperatures and igniting the quasar's fire. A heavy seed, thanks to its higher starting mass, could reach the supermassive range more swiftly, even with moderate feeding. A lighter seed, by contrast, would need either a stroke of fortune, such as an exceptionally dense inflow of gas, or perhaps a period of rapid, beyond normal accretion to make up for its late start. In either case, the growth process likely involved both continuous accretion and occasional mergers. As young galaxies merged with each other, a common event in the hierarchical assembly of structure, their central black holes could coalesce as well, stepping up in mass with each merger. We can imagine a chain of events: small black holes merging into bigger ones, gas streaming into galactic centers, and black holes swelling in mass year by year. Through these pathways, the seeds of darkness planted in the early universe might, within a few 100 million years, blossom into the luminous quasars we detect across billions of light years. The story of these seeds is fascinating, not only for what it tells us about black holes, but also for what it implies about the cosmos at large. The birth of the first quasars was a symphony of gravity and gas dynamics in young galaxies. It set the stage for a transformative effect on the environment. Once a quasar ignites, its intense radiation begins to interact with the surrounding matter. The light from the growing black hole streams outward, illuminating and ionizing the gas in its galaxy and beyond. In fact, it is through the imprint of that light on intervening material that we gather much of our knowledge about the early universe's gas. As we turn our attention to the space between galaxies, we will see how quasar light, traversing the void, reveals an intricate cosmic network of hydrogen clouds, the so-called Lyman alpha forest. These faint absorption signatures carry the story of the intergalactic medium that the first quasars grew up in, connecting the tale of black hole seeds to the grand tapestry of matter between the stars. When the light of a distant quasar journeys to Earth, it does not arrive untouched. Along the way, it encounters wisps of matter drifting in the intergalactic void, tenuous clouds of neutral hydrogen gas that inhabit the space between galaxies. Each time the quasar's light passes through one of these clouds, a particular fingerprint is left on its spectrum, an absorption line caused by hydrogen's Lyman alpha transition. Because these clouds lie at different distances, the associated absorption lines are imprinted at different wavelengths, each one redshifted according to the cloud's location in time and space. The result is remarkable. Instead of one shadow in the spectrum, we see dozens or even hundreds, a whole forest of absorption lines stretching blueward of the quasar's own Lyman alpha emission line. This is the famous Lyman alpha forest, a cosmic barcode that carries a wealth of information about the otherwise invisible intergalactic medium. Astronomers first became aware of this phenomenon in the late 1960s and early 1970s. Quasar spectra, when captured with sensitive instruments, showed an unexpected thicket of narrow absorption lines. In 1970, astronomer Roger Linds noted an unusually large number of such lines in the spectrum of a distant quasar, and correctly suspected that they all stemmed from the same atomic transition, hydrogen Lyman alpha, occurring in many separate clouds. Soon after, Jan Oort and other scientists realized these absorption lines could not be originating in the quasar itself, but rather were caused by intergalactic gas clouds between the quasar and us. Thus, the concept of the Lyman alpha forest was born, a direct observational proof that the empty space of the universe is threaded with diffuse, clumpy hydrogen gas. Each line in the forest is like a tree in a vast woodland, marking the presence of a gossamer cloud at a specific point in the cosmos. The physics behind these lines is straightforward, yet awe-inspiring. Neutral hydrogen atoms in a cloud can absorb light at the precise wavelength corresponding to the jump of an electron between its first and second energy levels, the Lyman alpha transition at 1216 angstroms. When quasar light encounters such atoms, photons at that wavelength get absorbed. But because the universe is expanding, a cloud's absorption will appear not at 1216 angstroms in the observed spectrum, but redshifted to a longer wavelength proportional to the cloud's distance. Consequently, a nearer cloud leaves an absorption line closer to the quasar's emission line, while a farther, hence earlier in time, cloud leaves its mark further to the blue in the spectrum. We end up with a continuous series of absorption lines, arranged by redshift, essentially a timeline of where the hydrogen clouds are along the line of sight. By decoding this pattern, astronomers can map out the distribution of intergalactic gas from the quasar to Earth. The Lyman alpha forest has proven to be an extraordinarily powerful tool for cosmology. These myriad tiny absorption lines carry statistical fingerprints of how matter is distributed on large scales. The spacing, density, and strength of the lines are not random. They reflect the clustering of matter, the ripples of the primordial density fluctuations that grew into today's cosmic web. By analyzing the forest's power spectrum, essentially the scale-dependent clumping of the absorption lines, researchers can infer the spectrum of density fluctuations in the early universe and test models of structure formation. In essence, the gentle dimming of quasar light by distant gas clouds encodes information about how those clouds and the dark matter halos hosting them are distributed across space. It is fascinating that one can study something as grand as the large-scale structure of the universe, using features as fine and faint as Lyman alpha absorption lines in quasar spectra. Moreover, the Lyman alpha forest provides a direct probe of the state of the intergalactic medium, IgM, through cosmic time. As the universe expanded and evolved, the diffuse hydrogen between galaxies went from a mostly neutral state to largely ionized. When we look at quasars at different redshifts, we see this change imprinted in their spectra. Quasars at moderate distances, say redshift 2 to 4, display rich forests of absorption lines, implying that by those times the IgM was thin and patchy, mostly ionized, with discrete neutral clouds scattered about. But if we push to higher redshifts, closer to the cosmic dawn, the forest thickens. The lines grow so numerous and so blended that eventually they blank out the quasar's continuum in that range entirely. This is a clue that we have reached the era before the intergalactic hydrogen was fully ionized. Indeed, observations of the Lyman alpha forest in very distant quasars have demonstrated that there was a time in the early universe when the pervasive hydrogen transitioned from neutral to ionized, the epoch of rionization. At redshifts above about 6, the forest gives way to what's known as the Gunn-Peterson trough, a sign that we are peering into a time when substantial fractions of the IgM were still neutral. Thus, the presence or absence of a Lyman alpha forest at various epochs allows us to chart when the cosmic fog of neutral gas was lifted by the first lights of stars and quasars. By exploiting the Lyman alpha forest, astronomers can even make maps of part of the universe's unseen gas. Each quasar provides a single line of sight, a pencil beam sampling of the cosmic web, often referred to as a skewer through the universe. But when many quasar spectra are taken across the sky, these skewers can be combined to create a three-dimensional picture. Large surveys like the Sloan Digital Sky Survey have gathered spectra of hundreds of thousands of quasars, and projects such as the Baryon Oscillation Spectroscopic Survey, BOSS, have specifically targeted the Lyman alpha forest in tens of thousands of quasars at redshifts around 2 to 3. The payoff has been revolutionary. Using this forest data, scientists have begun to construct 3D maps of intergalactic hydrogen on colossal scales, spanning billions of light years. These maps reveal the filaments and voids of the cosmic web, with the quasars acting as backlights. In these reconstructions, each Lyman alpha absorber marks a thread of gas stretching through space, and the absence of lines indicates vast voids where few atoms reside. We can actually see, through the prism of quasar light, the grand design of matter clustering that theory had long predicted. The universe's honeycomb-like network of filaments. Immersed in this tranquil forest of absorption lines, one cannot help but feel a sense of connection to the vast stretches of space between galaxies. The Lyman alpha forest is a subtle tracer, gentle dips in a graph, yet it speaks of enormous expanses filled with diffuse gas, of light travelling for billions of years and being dimmed ever so slightly by ephemeral clouds. It's a delicate, almost ghostly signal, but it has unveiled the hidden architecture of the cosmos. And within that architecture lie not just wispy filaments, but also occasional reservoirs of gas so substantial that they all but erase the quasar's light at certain wavelengths. These are the damped Lyman alpha systems, deep troughs in the spectrum corresponding to immense stores of neutral hydrogen. They are the oases of cold gas in the cosmic desert, and they play a crucial role as the fuel tanks for galaxies and black holes. As we continue, we will explore these massive reservoirs and what they tell us about the early diet of galaxies and quasars. Amid the fine filaments of the Lyman alpha forest, there occasionally loom much larger structures, immense clouds of gas that all but swallow the quasar's light at the Lyman alpha wavelength. These are the damped Lyman alpha systems, or DLAS, which appear as broad, deep troughs in the spectrum rather than narrow lines. By definition, a DLA is a cloud with an extremely high column density of neutral hydrogen, above about 2 × 10 to the 20 atoms per square centimetre. At such great column densities, the absorption line is not only saturated, letting essentially no light through at the line centre, but also extended by the natural broadening of the atom's spectral line, the so-called damping wings. This gives DLAS their name and characteristic appearance, a wide, smooth absorption feature that cuts deep into the quasar's continuum. When a quasar spectrum shows a DLA, it's a sign that a galaxy-sized quantity of cold hydrogen gas lies along our line of sight. Damped Lyman alpha systems represent the hefty reservoirs of fuel in the young universe. In fact, observations tell us that at redshifts around 2 to 4, an era when galaxies were rapidly forming stars, DLAS contained most of the neutral hydrogen in the cosmos. In other words, the bulk of all cold interstellar gas in that epoch was tied up in these massive, diffuse structures. Astronomers believe that DLAS are closely linked to forming galaxies. Essentially, they are the gaseous halos or extended protogalactic disks of young galaxies in the making. The column densities we measure in DLAS are comparable to those observed when looking through the entire thickness of the Milky Way's disk or other nearby galaxies. This suggests that a DLA sightline is akin to peering through a distant galaxy's reservoir of gas. Unlike the galaxies themselves, which might be too faint to detect in starlight at such distances, DLAS announce their presence boldly by absorbing the light of background quasars. In doing so, they provide a unique window into the distribution and kinematics of primordial gas on galactic scales. We can study how this gas is moving through Doppler shifts of the absorption lines, and even what it's made of through absorption lines of elements like carbon, oxygen, and iron embedded in the DLA. These cold, massive gas reservoirs are the raw material for future stars and for the growth of black holes. A DLA can be thought of as a cosmic fuel tank, a great store of neutral hydrogen that can cool and condense to form new stars within a galaxy, or feed a central black hole if the gas flows inward. In the context of quasars, one might envision that similar giant gas reservoirs in their host galaxies provided the sustenance for the supermassive black holes to grow. After all, a quasar's engine can only run as long as there is gas to accrete. The DLAS we observe along unrelated sightlines show that the early universe had plenty of such gas-rich reservoirs available. They likely dotted young galaxy halos, waiting either to fall into galaxies or to be blown out by the fiery feedback from star formation and active nuclei. Their chemistry also holds clues to the story of cosmic enrichment. Many DLAS contain detectable metals, elements heavier than helium, in their absorption spectra, indicating that they are not pristine gas, but have been enriched by previous generations of stars. By measuring the metallicity of DLA gas at different epochs, astronomers can infer how quickly galaxies were polluting their surroundings with the products of star formation. In a quasar spectrum, a damped Lyman alpha system is a striking feature. A calm, broad valley in the light, in contrast to the forest of sharp, tiny lines around it. It reminds us that not all hydrogen in the universe is confined to small wisps. Some of it resides in truly colossal clouds, large enough to influence galactic evolution. DLAS also serve as natural laboratories. Because they absorb quasar light, we can analyze the properties of star-forming gas in young galaxies without actually seeing the galaxies directly. This technique has yielded insights into galaxy formation theories, suggesting, for example, that many DLAS are the outer disks or gaseous halos of young, still-growing galaxies. Some DLAS have even been associated with visible galaxies in deep surveys, confirming that these absorption features indeed correspond to physical galaxies brimming with gas. While the Lyman alpha forest gave us a map of the tenuous cosmic web, the damped Lyman alpha systems highlight the densest pockets of that web, the places where gravity has pooled gas in large quantities. They act as cosmic reservoirs that would eventually fuel the lights of galaxies and quasars. And significantly, they demonstrate that by a few billion years into cosmic history, much of the intergalactic hydrogen had already been gathered into these reservoirs, leaving the remaining diffuse hydrogen largely ionized by the growing radiation background. In essence, DLAS mark the transition from the diffuse neutral fog of the very early universe to the more patchy, localized pools of gas in the later universe. Even as we marvel at these giant gas clouds, we recognize that they are signposts of a universe that is already partly illuminated. They appear in an epoch when many stars and quasars have formed and have kept most of space ionized, with neutral gas surviving only in dense pockets. But if we rewind further to an even earlier time, before these reservoirs coalesced and before starlight and quasar light had ionized the cosmos, we reach the cosmic dark ages when neutral hydrogen filled the intergalactic space more uniformly. When we look at the most distant quasars, we catch a glimpse of this bygone era. Their spectra show not just isolated damped absorbers, but a whole continuum of absorption, a Gunn-Peterson trough, indicating that the intervening space was saturated with neutral hydrogen. In the next part of our journey, we will see how this trough serves as a telltale beacon of the universe's transition from darkness to light, probing the end of the cosmic dark ages and the epoch of reionization. As we peer farther back in time through quasars, we approach an era when the cosmic fog of neutral hydrogen had yet to be fully burned away. The Gunn-Peterson trough is the hallmark of this primordial fog. It refers to a broad region of a quasar's spectrum where essentially no light comes through, a dark abyss in the graph of intensity versus wavelength, caused by nearly complete absorption of the quasar's ultraviolet light by intervening neutral hydrogen. In practical terms, if the intergalactic medium along the line of sight is even a few percent neutral, the multitude of overlapping Lyman alpha absorptions from all that hydrogen will coalesce into a continuous absorption, wiping out the quasar's flux over a range of wavelengths. This phenomenon was predicted in the 1960s by astronomers James Gunn and Bruce Peterson as a telltale sign of a largely neutral universe. For decades, quasars were only known at lower redshifts, showing the Lyman alpha forest and indicating an ionized IgM. But astronomers kept pushing to find more distant quasars hoping to catch the moment when the Gunn-Peterson trough would appear, the moment when quasar light finally encounters the lingering neutral gas from the cosmic dark ages. That moment arrived in the early 2000s. The Sloan Digital Sky Survey uncovered quasars at redshifts around 6 and beyond, and in their spectra, the long-anticipated trough was seen. In a quasar at redshift 6.3, for example, the spectrum blueward of the quasar's own Lyman alpha emission line was almost completely dark. A clear Gunn-Peterson trough, signaling that we were looking at a time when the intergalactic hydrogen was much more neutral than it is today. Subsequent discoveries, including an even more distant quasar at redshift 7.1, showed the same effect even more strongly. As one research team described, this quasar was far enough back in time that, for the first time, they could detect the signature of neutral hydrogen filling the space between galaxies. The existence of the trough had been predicted years earlier, but seeing it in data was like discovering a new continent on the map of the universe. It was a direct confirmation that by those epochs, when the universe was a few 100 million years old, significant patches of hydrogen were still unionized. The Gunn-Peterson trough provides a window onto the epoch of reionization, the transitional period when the first luminous objects, stars, galaxies, and quasars, flooded the universe with energetic photons and transformed the primordial dark, neutral intergalactic medium into the ionized one we observe at lower redshifts. When we observe a trough in a high Z quasar spectrum, we are essentially witnessing a time when the cosmic dawn was still breaking, when islands of neutral gas had not yet been fully penetrated by ultraviolet light. By analyzing how the residual light, if any, tapers off in the trough, scientists can estimate the fraction of hydrogen that remained neutral at that epoch. The quasars around redshift 6 to 7 indicate that the neutral fraction of the IgM was rising rapidly with redshift. Quasars at Z, approximately 6, about 12.7 billion years ago, show little to no transmitted flux shortward of Lyman alpha, implying that the intergalactic hydrogen was almost entirely ionized by that time, with only tiny pockets of neutral gas remaining. In contrast, quasars deeper in time, Z greater than 6.5, show even more extended dark gaps, suggesting a significantly higher neutral fraction, meaning we are observing the universe when reionization was not yet complete. In effect, the trough lengthens and darkens as we venture closer to the cosmic dark ages. One quasar at redshift 7.1, ULAS J1120 plus 0641, the one discovered by Dr. Mortlock's team, famously revealed a Gunn-Peterson trough that was profoundly black, indicating a substantial amount of neutral hydrogen still present when the universe was only 770 million years old. This observation provided evidence that we were indeed crossing the boundary between a reionized universe and the preceding neutral era. It marked the first detection of substantial neutral intergalactic gas, since that gas had been ionized in the first galaxies. From such observations, astronomers infer that the tail end of reionization likely occurred around Z, approximately 6 to 7. Prior to that, the cosmos was in its dark ages, starless at first, and then lit only sparsely by the earliest stars and proto-galaxies, whose radiation gradually ate away at the neutral hydrogen mist. The Gunn-Peterson trough is essentially a shadow cast by that mist. When we see the shadow, we know the mist was still there. Interestingly, the presence of the Gunn-Peterson trough in those earliest quasars also underscores the role of different light sources in cosmic reionization. Quasars are incredibly bright, but they were rare in the early universe. The fact that reionization was largely completed by Z, approximately 6, suggests that it was not driven primarily by quasars, but rather by the far more numerous galaxies and their stars. Current analyses indicate that the combined ultraviolet output of countless hot young stars in early dwarf galaxies probably provided the majority of photons that ionized the IgM, with quasars contributing a smaller share. Quasars, however, serve as superb beacons to confirm and probe this process. Their spectra carry the imprint of ionization's progress. In the darkness of a Gunn-Peterson trough, we find confirmation that we have reached back to the era when the cosmic fog was lifting. It is striking that even darkness itself, manifested as the trough in a quasar's spectrum, can serve as a message from the past, telling us exactly when the first light of stars and galaxies finally chased away the cosmic night. As the universe continued to expand and more sources of light turned on, the Gunn-Peterson trough eventually disappears from view in later quasars. By redshift 5.5 or so, quasars once again exhibit a Lyman alpha forest of discrete lines rather than a solid trough, telling us that the IgM had become almost completely ionized, and neutral gas was confined to isolated pockets or dense clouds. Thus, the Gunn-Peterson test, the search for that trough, delineates the end of the cosmic dark ages. It signals that we have reached the time when the first generations of stars and galaxies brought dawn to the universe. With this powerful method, we turn the blinding absence of light into a tool for understanding how and when the young universe emerged from darkness. Having identified the epoch when the cosmic gas went from opaque to transparent, we can now ask, what became of that gas once it was ionized and enriched by the first stars? How did those early generations of star formation spread heavier elements into intergalactic space? The quasars, again, provide answers. In the spectra of these distant beacons, beyond the hydrogen trough, lie subtle fingerprints of elements like carbon, silicon, and oxygen. These metals in the void tell a story of how the products of stellar alchemy were dispersed across space. In the next section, we will trace these metallic clues and see what they reveal about the circulation of matter, how the light from quasars exposes not only hydrogen, but the ashes of the first stars strewn throughout intergalactic space. When we examine the intergalactic medium, not just for hydrogen, but for other elements, an intriguing story emerges. The cosmic void is not truly pristine. Scattered throughout the faint absorption features of quasar spectra are signatures of heavier elements, metals forged in the hearts of stars. For instance, a cloud that produces a Lyman alpha absorption line might also imprint a much weaker line from ionized carbon C4 or silicon Si4 at nearby wavelengths. The very presence of these metal lines in the intergalactic forest tells us that the gas there has been polluted by materials from stars. These elements cannot have originated in the void itself. They are the ashes of stellar alchemy that have been cast out of galaxies. By around redshift 3, about 11 to 12 billion years ago, virtually every corner of the low-density intergalactic medium shows at least traces of heavy elements ui.ads, abs.harvard.edu. Observations reveal that even the most tenuous hydrogen filaments, those with the thinnest Lyman alpha lines, often contain detectable amounts of carbon or oxygen. In other words, by that time the cosmic web had been thoroughly seasoned with the products of star formation. The once virgin hydrogen of the universe's youth was, by a few billion years in, enriched with bits of carbon, oxygen, silicon, and iron from early generations of stars. This widespread enrichment is a profound clue to the history of galaxies. It implies that the galaxies of the young universe did not retain all their matter. They drove some of it out. The leading explanation is galactic winds, streams of gas propelled out of galaxies by the energy of supernova explosions, and perhaps the radiation or jets from young quasars. When massive stars in early galaxies ended their lives in supernovae, they blew out not only light and energy, but also their elemental debris. Entire gaseous shells, loaded with freshly made heavy elements, would have rushed outward at hundreds of kilometers per second, escaping the shallow gravitational wells of infant galaxies and spilling into intergalactic space. Over time, these winds from many galaxies would overlap and fill the space between galaxies with a diffuse froth of metals. This scenario is strongly supported by observations. Metal absorption lines are often found far from any obvious galaxy, which would hardly be possible unless those metals had been carried there by outflows. Thus, even as galaxies were assembling, they were also pollinating their surroundings with the chemical products of their stars. The cosmic web became enriched in a patchwork fashion as each galaxy blew bubbles of metal-rich gas into the void, which eventually burst and mingled, raising the background level of heavy elements everywhere. We can trace this enrichment by studying quasar absorption spectra in detail. Carbon is a common tracer. The triply ionized carbon line, C4, at 1,548 angstroms and 1,550 angstroms in the rest frame, is often used to gauge intergalactic metallicity. By looking at the strength and frequency of C4 lines associated with Lyman alpha forest clouds, researchers can estimate the typical abundance of heavy elements in those clouds. They find that by redshift 3, the diffuse IgM has a metallicity on the order of 1,000th to 1/10th of the Sun's abundance, small but definitely non-zero. Even at higher redshifts, closer to the epoch of reionization, there are glimpses of metals. In the spectra of the most distant quasars, redshifts above 6, astronomers have identified faint absorptions due to elements like carbon and oxygen. These absorbers are probing the products of the very first generations of stars. The fact that we see, for example, C4 absorption in a quasar at redshift 7 means that some of the earliest massive stars had already lived, died, and dispersed their carbon into the surrounding gas by the time the universe was only a few 100 million years old. It's a remarkable thought. Even as the universe was barely out of its dark ages, it had already been seeded with the chemical fingerprints of stars. Quasars themselves add to this narrative. The emission spectra of quasars, the light coming from gas in the immediate vicinity of the supermassive black hole, show strong lines of elements like carbon, magnesium, and iron. Early quasars do not shine from primordial gas alone. Their light must filter through gas that has been enriched by stars in their host galaxies. In fact, analyses of quasar broad emission lines indicate that some high redshift quasars have surprisingly high abundances of elements like iron, implying that a vigorous phase of star formation occurred in their galaxies, producing iron in supernovae, before or concurrently with the quasar's appearance. This dovetails with what we see in absorption. By the time we observe a fully formed quasar, its galaxy has already had time to forge substantial numbers of stars and pollute both its internal environment and the surrounding intergalactic medium with metals. The distribution of metals in the IgM provides insight into how uniformly or patchily the early enrichment occurred. It appears that while some regions of the intergalactic space, especially those near clusters of galaxies, have relatively higher metallicity, even the voids are not completely pure. Over billions of years, gravity will draw some of that enriched gas back into galaxies or into the filaments, and fresh winds will push metals out again in a great cosmic circulation of matter. The quasar absorption lines serve as tracers of this cycle. Each detection of a metal line in the void is like a message in a bottle from an ancient star, telling us it lived and died, and its ashes travelled far. By mapping metals in quasar spectra at various redshifts, we effectively chart the progress of cosmic chemical evolution. We see a steady increase in metallicity over time, little to none at the very dawn, as expected when only pristine gas existed. then the first trickle of metals from the earliest stars, and by redshift 3, a widespread enrichment that continues to rise toward the present day. It is humbling to realize that even the emptiest expanses of intergalactic space are dappled with atoms of carbon and iron from stars long extinct. The void is not empty. It carries a memory of all the stellar furnaces that have burned. Having followed the journey of heavy elements from galaxies into the intergalactic medium, we are reminded that quasars illuminate these processes for us. Their light, crossing billions of light years, can encounter both the primordial hydrogen and the later added metals, revealing both the state of the universe's matter and its history of star-driven change. Now, turning our focus back to the quasars themselves, we consider how their intense radiation influences their immediate environments. Just as galaxies blow metals outward, quasars carve out ionized zones around them. In the next section, we will explore the proximity zones of quasars, regions where their powerful light has stripped electrons from atoms in their vicinity, forming bubbles of ionization in an otherwise neutral medium. These proximity effects offer further clues about how quasars interact with the universe around them in those early epochs. In the epoch when neutral hydrogen still permeated much of space, a quasar did not shine into a uniformly ionized medium. Instead, its fierce ultraviolet radiation had to drill a cavity in the surrounding hydrogen, a local bubble of ionization expanding outward from the quasar like a mini cosmic sunrise. This region is known as the quasar's proximity zone, or near zone, where the quasar's photons have stripped electrons off the hydrogen atoms around it, turning a once opaque environment into a transparent one. One can almost picture the ionization front racing outward from the quasar, a luminous wave expanding into the neutral cosmic night, like a hot knife cutting through fog. Within this bubble, the quasar's light can travel relatively unimpeded, so we see flux in the spectrum. Beyond it, if the intergalactic gas is still neutral, the light is abruptly absorbed and we enter the Gunn-Peterson trough. The transition is dramatic. Looking at a high redshift quasar spectrum, one often sees a stretch of transmitted light just blueward of the quasar's Lyman alpha emission line, perhaps dotted with a few remaining absorption lines, and then a sudden plunge to darkness. That glowing stretch is the quasar's proximity zone, the direct imprint of the quasar's ability to ionize its neighborhood. The size of a quasar's proximity zone is a measure of its impact on its environment. Several factors set the scale of this ionized bubble. First is the quasar's luminosity in ionizing ultraviolet light. A more powerful quasar emits more ionizing photons per second and can thus ionize a larger volume of space. Second is the length of time the quasar has been shining, its age or lifetime. An older quasar has had more time to blow up a big bubble, whereas a quasar that only recently turned on will have a smaller sphere of influence. Third is the ambient density and neutrality of the surrounding intergalactic medium. If the IgM is mostly neutral and dense, it will quench the expansion of the ionized zone more quickly, whereas a pre-ionized or low-density IgM offers less resistance. All these factors combine so that the observed proximity zone size can tell us something about both the quasar and the universe around it. For a given quasar brightness, a smaller than expected proximity zone might hint that the quasar is young, it hasn't yet reached equilibrium with its environment, or that the IgM is more neutral than assumed, or both. Conversely, a large proximity zone suggests either a long-lived quasar or an already ionized surrounding medium. Astronomers have measured the proximity zones of the highest redshift quasars and gleaned insights about the tail end of ionization from them. For example, quasars at redshift about 6 typically show proximity zones of a few megaparsecs, several million light-years, in radius, after accounting for their luminosity. As we push to quasars at redshift 7, their proximity zones, once adjusted for brightness, tend to be smaller. This trend aligns with the expectation that the IGM was more neutral at earlier times. The quasar's bubble was squeezing into a denser neutral medium and couldn't grow as far. In effect, the shrinking proximity zones at higher redshift are another indicator that we are observing closer to the epoch when cosmic hydrogen was not yet fully ionized. There is also significant scatter in the sizes of proximity zones among different quasars at the same redshift, which can be interpreted as differences in quasar lifetimes or local environments. A few quasars have strikingly small near zones, too small to be explained by cosmic neutrality alone. In those cases, astronomers suspect the quasar may have turned on only recently, perhaps within the last 100,000 years or so, and thus its light has not had time to push the ionization front much farther out. Such observations are exciting because they may represent quasars in an early stage of development, giving us a direct window into the timing of quasar ignition. The concept of the proximity zone beautifully illustrates how a quasar is not merely a passive light source, but an active agent of change in its surroundings. These objects are so luminous that they substantially alter the state of matter tens of millions of light-years away. During the final phases of reionization, as pockets of neutral gas lingered, each new quasar that flared into life effectively lit a candle in the darkness, creating a spherical haven of ionized gas around itself. Eventually, as more and more candles were lit by stars and quasars, the individual bubbles overlapped and merged into a fully illuminated cosmos. Quasar proximity zones thus capture a universe mid-transformation, a patchwork of ionized bubbles within a neutral sea. By studying them, we observe reionization not as a single global switch, but as a local, stochastic process happening around each source of light. Even after reionization was complete, the proximity effect of quasars can be observed in a subtler form. In a later, mostly ionized universe, a quasar still enhances the ionization level of gas in its vicinity above the cosmic average. In spectra, this manifests as a slight thinning of the Lyman alpha forest near the quasar's emission line. Fewer or weaker absorption lines because the quasar's own radiation has reduced the neutral fraction of hydrogen locally. This effect, observed in lower redshift quasars, was historically one of the first pieces of evidence that the intergalactic medium is ionized by a background radiation field, the UV photons from galaxies and quasars. The quasar essentially adds to that background, clearing out additional hydrogen in its neighborhood, hence proximity effect. In the high redshift context, however, the term proximity zone usually refers to the dramatic case of a quasar carving out a distinct ionized bubble during reionization. The study of quasar proximity zones at the end of the Dark Ages is still evolving. With next-generation telescopes, astronomers hope to find even more distant quasars and measure how their bubbles grew. This will refine our understanding of both quasar physics, like how long and steadily they shine, and the timeline of reionization. Each newly discovered quasar at extreme distance is like a lighthouse whose immediate surroundings tell a story about the dawn of the universe. In their own way, these proximity zones are akin to cosmic beacons illuminating the conditions of their time. By combining all these threads, from redshift and look-back time to early supermassive black holes, from the forest of hydrogen lines to the metal enrichment of the cosmos, and from the neutral hydrogen troughs to the ionized bubbles around quasars, we assemble a picture of a universe in flux. But the story of quasars does not end in the early epochs. As the universe matured, the mighty quasar epoch subsided. The titanic black holes of the distant past eventually ran low on fuel or went dormant, and the torch was passed to more modest, local active galaxies. This shift in cosmic activity is often referred to as cosmic downsizing. In our next section, we will explore how quasar activity changed over time, how the blazing giants of the young universe gave way to a quieter cosmic landscape, and what that tells us about the life cycle of galaxies and black holes. As the universe aged beyond its turbulent youth, an interesting shift took place in the cosmic stage show of quasars. The brilliant beacons that dominated the early epochs became rarer, and the frenetic growth of supermassive black holes began to slow down. Astronomers who survey the population of quasars at different times have discovered a clear pattern. The most powerful quasars had their heyday in the distant past, while in later times only smaller-scale active galaxies continue to flicker. This phenomenon is often described as cosmic downsizing. In effect, the large players, the giant black holes gobbling gas at ferocious rates, went first, having their peak activity billions of years ago, whereas the smaller black holes in more modest galaxies peaked later or are only active now. Observationally, quasar numbers and luminosities reached a maximum around a redshift of about 2 to 3, roughly 10 to 11 billion years ago, which is often called the quasar epoch. At that time, quasars were hundreds of times more common and more luminous than in the present universe. Since then, the abundance of quasars has declined dramatically. By redshift 1, about 8 billion years ago, the extremely luminous quasars had mostly faded, and by today, spectacular quasars are exceedingly scarce. In tandem with this decline in quasar numbers is a change in the typical scale of active galactic nuclei. Surveys of active galaxies find that high luminosity AGN, the kind powered by the most massive black holes, similar to quasars, were far more prominent in the early universe than now, whereas low luminosity AGN, powered by smaller black holes, are relatively more common in the later universe. In other words, the cosmic quasar population downsized. The big guns shot off early, and the pop guns kept firing later. For example, X-ray and optical studies show that very bright quasars peaked in abundance at redshifts around 2, while much fainter active nuclei peaked closer to redshift 0.7, approximately 6 billion years ago. By that more recent epoch, the universe's most massive black holes had largely run out of fuel or settled into dormancy, and only the smaller mass black holes in smaller galaxies were still gradually accreting and shining. This shift in activity reflects the changing circumstances of galaxies over cosmic time. In the early universe, gas was plentiful, and galactic environments were conducive to funneling large amounts of fuel onto black holes. Galaxy mergers were frequent, and those collisions could drive gas to galactic centers, triggering both bursts of star formation and feeding the central black holes. It was an era of exuberance, hence the copious quasars and the rapid growth of giant black holes. But as time went on, the universe expanded and evolved. Galaxies grew in size and virialized. Many exhausted or expelled their easy supplies of cold gas. The huge black holes that had formed early had by then consumed or heated the lion's share of available fuel in their vicinity, often quenching further infall of gas through the energy they released, a process known as feedback. In massive galaxies, any remaining gas might be too hot or too diffuse to accrete efficiently. As a result, those once brilliant quasars faded, leaving behind dormant supermassive black holes, like silent embers where a roaring fire once burned. We see their remnants today in galaxies like the Milky Way and giant ellipticals, enormous black holes that are either quiet or only weakly active, such as our galaxy's central black hole, which now barely emits any radiation. Meanwhile, smaller galaxies, which initially had smaller black holes, often had a longer, more gradual supply of gas. Some continued to form stars and trickle-feed their central black holes well into later epochs. Thus, in the more recent universe, one finds mostly moderate or low luminosity active galactic nuclei, like Seyfert galaxies and radio galaxies, rather than ultraluminous quasars. This is why the typical active galaxy in the nearby universe, say a Seyfert galaxy in the local supercluster, has a black hole of maybe a few million to 100 million solar masses accreting at a modest rate, whereas the typical active galaxy at redshift 2 was a quasar with a black hole of 1 billion solar masses devouring matter at the maximal rate. The overall cosmic energy output from accreting black holes has declined by orders of magnitude since the quasar epoch. The torch of activity has essentially passed from the giants of yesterday to the dwarves of today. The term downsizing might sound paradoxical in a universe that otherwise grows structures hierarchically, small things merging to form big things. In a sense, big black holes did form early via that hierarchical process, but once they formed, they consumed available resources and then went quiet. Smaller black holes, in smaller galaxies or in less dense regions, were slower to ignite and could continue growing or accreting at lower levels for a longer time. Another way to look at it is that the peak growth period for objects correlates inversely with their mass. The most massive black holes achieved their peak growth in the early universe, whereas intermediate mass black holes peaked later. This pattern is mirrored in galaxy evolution as well. Massive galaxies formed their stars early and rapidly, and then mostly stopped becoming old, red ellipticals, while smaller galaxies continued forming stars up to more recent times. The quenching of star formation in large galaxies early on, and the continued star formation in smaller ones, is a form of downsizing in galaxy evolution that parallels the AGN downsizing. Our own cosmic neighborhood exemplifies the quiet aftermath of the quasar age. Today, the night sky does not contain any object as luminous as a quasar to the naked eye. The quasars we study reside billions of light years away, seen in the distant past. Locally, we have many galaxies harboring dormant monsters. For instance, M87 in the Virgo cluster has a black hole weighing several billion suns at its center, which in the past likely powered a quasar or a powerful radio galaxy. But now it is relatively subdued, only noticeable by a jet and radio emission. The Milky Way's central black hole is comparatively small, about 4 million solar masses, and currently quiet, though it likely was more active in the past. Active galactic nuclei in the present epoch are generally feeble in comparison to the quasars of old, yet they remind us that the engine is still there, just idling. Cosmic downsizing has implications for the large-scale tapestry of the universe. It means that the peak of energy injection into the cosmos from quasars, in the form of radiation and kinetic feedback, happened early. Quasars heated and stirred the intergalactic medium more strongly in the past, whereas recent eons have seen a more gently evolving IGM. It also means that if one were to look at the universe at a quarter of its current age, the most prominent beacons would be different from those now. The universe gradually transitioned from a quasar-lit blaze to a calmer, galaxy-lit glow. The once dominant quasars have ceded the throne to billions of normal galaxies, whose combined starlight now dominates the optical brightness of the universe, and to the diffuse radiance of myriad lower-power AGN. Yet, the legacy of those early quasars endures. The supermassive black holes they grew remain at the centers of galaxies, and their influence is still felt in the structural and kinematic properties of their hosts. And importantly, even though the cosmic drama of quasars has quieted down, those that shone long ago have left markers across space, from the heat added to intergalactic gas, to the metals distributed across the universe, to the sheer gravitational influence their black holes exert. In the final section of this part, we shift perspective to these large-scale imprints and arrangements. We will see how quasars, past and present, act as landmarks in the grand design of the cosmos, the cosmic web of galaxies and gas. They trace the densest knots and filaments of large-scale structure, guiding us in mapping the universe's vast architecture and revealing the threads of the cosmic web that connect galaxies over billions of light years. Seen from a great distance, quasars appear as solitary points of light. But in reality, they are embedded in the cosmic web, the vast foam-like structure of matter that spans the universe. Quasars tend to reside in the densest knots of this web, marking the locations of massive galaxies and clusters. Where we find a high redshift quasar, we often find a convergence of filaments and an abundance of galaxies. In fact, quasars act as beacons, highlighting the nodes of large-scale structure. Astronomers mapping the distribution of quasars have noted that they are strongly clustered. Quasars are more likely to be found near other quasars or rich galaxy environments than in isolation. This reflects the simple truth that a quasar requires a massive host galaxy and black hole, both of which form preferentially in the deepest gravitational wells. Thus, quasars trace the skeleton of dark matter and galaxies that is the cosmic web. If we imagine a map of the universe with its filaments and voids, the quasars would light up along the filaments like city lights along highways, delineating the infrastructure of the cosmos. Distant quasars, in particular, have been used to probe the large-scale structure in the young universe. In some cases, astronomers have discovered groupings of quasars that span enormous distances. One example is the so-called Huge Large Quasar Group, an alignment of 73 quasars over a region roughly 4 billion light-years across. Such an immense feature pushes the limits of what our cosmological models can readily explain, sparking debate about whether the universe is truly homogeneous on the largest scales. Structures of such scale push the limits of our cosmological models, raising questions about how such a giant assembly could have formed. While it's possible that some of these large quasar groupings are statistical flukes or lines of sight through extended filaments, they undeniably show that quasars are excellent tracers of where matter is concentrated on grand scales. Another discovery showed quasars seeming to align. Observations with the Very Large Telescope found that the rotation axes of quasars in a huge region of space tended to point in similar directions, and these directions were aligned with the large-scale cosmic filament they inhabited. It is as if the quasars not only inhabit the cosmic web, but are also influenced by its directional threads, a cosmic alignment spanning billions of light-years. Even on somewhat smaller scales, quasars flag the presence of forming clusters and protoclusters. When we zoom in on the environment of a high redshift quasar, we frequently find a surfeit of galaxies around it. For example, a quasar might sit at the center of a protocluster of young galaxies. Those galaxies may be faint and hard to detect, but deep surveys in various wavelengths, infrared, submillimeter, etc., often reveal them around the quasar, all sharing roughly the same redshift. This suggests that the quasar is a member of a developing cluster of galaxies, perhaps the future core of a massive cluster we see in the local universe. The quasars are like signposts planted at these busy intersections of the cosmic web, signaling, "Here be a great city of galaxies under construction." In the modern universe, although quasars are much rarer, we continue to use active galactic nuclei as tracers of structure. For instance, certain galaxy clusters host radio-loud AGN, at their centers, and those can be used to pinpoint clusters in sky surveys. Moreover, quasars and AGN in general are part of the large-scale structure maps that cosmologists create. The Sloan Digital Sky Survey mapped the three-dimensional positions of tens of thousands of quasars, extending the cosmic web cartography out to distances of 12 billion light-years. These maps show the same patterns of filaments and voids that galaxy surveys do, with quasars often sitting in the prominent peaks of the density field. On the largest scales, matter is arranged in a roughly homogeneous cosmic web, and quasars simply highlight the densest nodes of that arrangement. The relationship between quasars and large-scale structure is reciprocal. Not only do quasars occur in certain places in the cosmic web, but they also can impact that web. Powerful quasar outflows and jets can inject energy and momentum into the surrounding gas, stirring it and possibly helping to keep it ionized or blowing it out of galaxies into the intergalactic medium. In clusters of galaxies, AGN feedback from central quasars or radio galaxies is thought to help prevent gas from cooling too quickly, thus influencing the future star formation in those clusters. In that sense, quasars are not just passively marking the structure, they are active participants in shaping the evolutionary pathways of the cosmic web's nodes. The heating from many quasars over time could even smooth out some of the intergalactic medium or quench star formation in small satellite galaxies. The cosmic web we observe today, with its mix of fertile and barren regions, may bear the imprint of those quasar episodes long ago. Quasars as landmarks of large-scale structure also help us navigate the universe in a more literal way. Because quasars are so bright and can be seen across the cosmos, they serve as reference points for astronomers. An entire celestial coordinate system, the International Celestial Reference Frame, ICRF, is defined by the positions of distant quasars, which are effectively fixed on the sky. Their immense distances make their proper motions negligible, so they act like nearly immutable beacons against which we measure the motions of nearer objects. In this practical sense too, quasars are guide stars, anchors for our maps of the heavens. From the tiniest scale of a black hole's event horizon to the expanse of the cosmic web, quasars provide insight at every level. In this part of our documentary, we followed quasars from being lighthouses of the early universe to tools for probing intergalactic gas and the growth of structure. These brilliant objects connect the story of galaxies to the story of the universe at large. They showed us how looking at a single point of light can reveal the composition of the intervening space, the timing of cosmic dawn, the behavior of matter across billions of light years, and the evolution of galaxies over eons. And yet, there are even more facets to the quasar story, from the extreme physics near their central black holes, to their multi-wavelength manifestations, and the mysteries of how they ignite and fade. As we continue our journey, the quasars remain our luminous companions, shedding light on the dark and distant reaches of space-time and guiding us deeper into the cosmic mysteries ahead. Quasars, once enigmatic curiosities, have become guiding lights in our quest to understand the cosmos. And as we push further, they will continue to shine, beacon-like, revealing whatever cosmic wonders remain to be discovered.